Your Excellencies, distinguished audience, ladies and gentlemen, welcome to the International Workshop on the Future of Seawater Agriculture and Saline Agriculture in the Kingdom of Saudi Arabia. The Kingdom of Saudi Arabia is very ambitious to achieve self-sufficiency in food production. However, the challenges of desertification, hot, dry climate, water scarcity, poor soil fertility, and lack of employment, in addition to food security risks in vast geographical areas, generated the will to face obstacles and achieve sustainable development of agriculture in the Kingdom of Saudi Arabia. In this regard, a sustainable food production system is indispensable for economic growth, rural development, environmental sustainability, and food and nutrition security. Restructuring agricultural production in such areas through the introduction of innovative production systems is imperative to meet the challenge of producing 70% more food and fiber by 2050. New opportunities lie in modern technologies based on newly developed knowledge and advanced management of natural resources backed by policies that are innovative and robust methods for designing, implementing, and assessing detailed development pathways through flexible thinking approaches. In this regard, biosaline agriculture, especially seawater agriculture, has emerged to contribute to the resistance to climate change and as an innovative production system for sustainable food production in such areas. Several activities over the time period have produced a large number of innovative knowledge and technologies about potential opportunities to further support food production systems in the Kingdom of Saudi Arabia, that is surrounded by the Red Sea in the west and the Arabian Gulf in the east, with thousands of kilometers. It is very important to promote solutions tailored to development of seawater and biosaline agriculture in the world and the Kingdom of Saudi Arabia to contribute to food security. Distinguished audience, welcome again. First of all, we will have His Excellency Engineer Ahmad bin Saleh Aid Al Kuji, Deputy of Ministry of Environment, Water and Agriculture to the Kingdom of Saudi Arabia. The floor is yours, Your Excellency. In the name of Allah, the most gracious, the most merciful, peace, mercy and blessings of Allah be upon you all. I welcome you all, the participants, to the first international workshop on the future of biosaline agriculture and techniques and technologies of seawater agriculture in the Kingdom of Saudi Arabia, which is hosted by the Ministry of Environment, Water and Agriculture, with the participation of about 14 experts, consultants, and speakers coming from 11 countries worldwide as part of its efforts to organize such workshops. These international workshops aim to identify the future of saline agriculture and learn about countries' experiences in using agricultural techniques and technologies through the exploitation of saline water to contribute to achieving sustainable development goals. The global agriculture sector is now facing many challenges, which are represented in the high rates of land salinization and the deterioration of its characteristics, in addition to the continued decrease in the areas of arable land and the steady increase in the population. In light of such challenges, especially in the conditions of climate change, the farming agricultural techniques using seawater One of the solutions may be to meet part of the demand for food through the exploitation of saline water and marshlands in such a way that presents the sustainability of natural resources. In recent decades, the world has made progress in the use of seawater farming techniques, but these technologies are still under research and development and need more attention and support, and opportunities to improve them are still continuing to find more solutions that may support agricultural production under such difficult economic conditions. It is certain that agricultural technologies become sustainable only if technological innovation is in line with the real global challenges and provides effective, viable, low-cost, easy-to-implement and accessible solutions. Accordingly, we see that there are many opportunities that allow the use of saline water and seawater to support the agriculture sector through the development of systems for its use and exploitation in many areas, such as cooling greenhouses and cultivating crops that are highly tolerant to salt stress as a genetic source that supports agriculture production. In conclusion, I would like to emphasize the importance or re-emphasize the importance of studies showing modern systems, technologies, and innovations, including biosaline farming techniques and the use of seawater in agriculture through more global, regional, and local partnership to achieve tangible progress in developing them and improving the economics of their production. Equally important, I ask Allah to successfully guide you through the work of this workshop with success and reward, and I hope that your meeting will achieve this hoped-for goals to be catalyst for food production and the achievement of sustainable development goals. Thank you so much, Your Excellency, Deputy of Ministry of Environment, Water and Agriculture, for your inspiring keynote speech. Now, let's move to Dr. Sulaiman Ali Al-Khatib, Director General of the General Department of Plant Wealth at the Ministry of Environment, Water and Agriculture in the Kingdom of Saudi Arabia to manage the sessions of this international workshop on the future of hydroponics, saline agriculture and farming technology using seawater in the Kingdom of Saudi Arabia. Now, we will invite you all to watch a short video clip on saline agriculture in the Kingdom of Saudi Arabia, and then we will return to Dr. Sulaiman and the discussion sessions to moderate the sessions or panel discussion in the workshop. To enhance food security through agricultural production projects and their production efficiency, and in order to present an integrated research model for the production of vegetables and fish in a closed system for recycling and desalination of seawater, and as a result of conducting research for 5 years, the Agriculture Deputyship at Ministry of Environment, Water and Agriculture established a research unit project for seawater agriculture as the first country to succeed in establishing such a project. Exploiting the waters of the Red Sea, of course, in food production and providing a model to encourage investors to use modern and energy-saving technologies and promote agriculture development in coastal regions through the establishment of a research unit based on reducing water waste and energy costs. The project is characterized by the following: reliance on seawater in agriculture completely, without using any other water resources, relying on seawater for cooling of greenhouses, using basalt walls for cooling, and operating the entire system based on solar energy using 3 systems in agriculture, namely traditional seawater agriculture, hydroponics, and aquaculture in all agriculture systems, and aquaponics, integrative agriculture between fish and plants. A project which is based to produce tomatoes, or did produce actually tomatoes, green peppers, lettuce, mint, basil, two types of fish, that is barramundi fish and tilapia fish, the best production ever. Also, during the past experiences and experiments, the success of cooling system was studied in light of the changes in temperature and humidity throughout the season. The research unit aims to develop studies and experiments based on seawater agriculture.
Thank you very much, Your Excellency, Engineer Ahmed bin Saleh Al-Iyada, for this speech, and I'm very grateful and thankful for your support and your guidance to hold this international workshop in seawater farming and saline agriculture in the Kingdom of Saudi Arabia. Distinguished speakers and esteemed participants, experts, and attendees. It is my honor to welcome you all virtually from the Kingdom of Saudi Arabia to the host such a distinguished gathering for this international workshop in the future of seawater farming and saline agriculture in the Kingdom of Saudi Arabia. I express my gratitude for our partners, King Faisal University, King Abdulaziz City for Science and Technology, and King Abdullah University of Science and Technology to highlight the importance of seawater farming and saline agriculture by facilitating us to organize such a wonderful virtual event. In addition, I would wish to take this opportunity to extend my sincere gratitude and appreciation to all the participants for their contribution and their valuable presentation, which will be shown shortly. I hope this international workshop will proceed towards valuable outcomes. As you know, globally, we are facing food security and sustainability challenges. Moreover, biotic and abiotic stresses, along with dry land and saline conditions, under the implications of climate change, adding complexity to our food system and to our food production. These challenges demand renewed interest and focus to explore and invest on the research and development of such avenues that could contribute sustainably to our food production system. Although the concept of biosaline agriculture dates back to 1979, but it has become more relevant now due to abundance of saline soils as per FAO latest report complying the data of 118 countries, which revealed that 424 million hectares of topsoil and 833 million hectares of subsoil are salt affected. Our main objective to organize this workshop is to highlight the challenges and proposing pathways in the context of innovations by knowledge sharing and success stories of different crop grown to promote seawater farming and saline agriculture here in Kingdom and in the world. In this regard, I'm happy to share that we have a great gathering of professionals and scientists and government officials from different regions of the world to present scientific advancement, novel technologies, and innovations in the field of seawater farming and saline agriculture that would contribute to sustainability and resilience to global food production systems. We have divided this workshop in 3 technical sessions. In the first session, we have 5 keynote speakers affiliated with different institutions from Kingdom Saudi Arabia, USA, United Arab Emirates, Italy, Australia, and Netherlands. They will express their views and present expert opinion about the seawater farming and saline agriculture challenges and scientific advances. I highly appreciate your cooperation and help to make our workshop successful by limiting the time to 10 minutes, please, maximum, so that we can timely manage and moderate the session. The questions and answers will, with our expert will be at the end of each session. I'm happy to invite our first speaker, Dr. Rod Wang, to present in Neo-Domestication, developing a new crop from native plants. He is basically affiliated with Arizona Genomic Institute, University of Arizona, USA, and currently he is serving as a director of the Center for Desert Agriculture, King Abdullah University of Science and Technology, Saudi Arabia. He is mainly focuses on the discovery and utilization of nurture variation to create a digital gene bank to accelerate the breeding of target varieties that could adapt the desert environment of the Middle East. Dr. Rod, your mic is yours for 10 minutes and proceed, Doctor. Thank you very much.
Okay, good. I want to go to the first slide. Sorry. Okay, good. Can everybody hear me okay? Okay. Thank you. Good morning, good afternoon. It's 2 o'clock in the morning for me in Tucson. So it's great to be here. I want to thank the organizers for inviting me to speak today. And I'm representing KAUST today. And next slide. The title of my talk is Neo-Domestication, Developing New Crops for Native Plants. Next slide. I'm going to talk a couple minutes about the Center for Desert Agriculture, and then I'll move into my research topic. So I'm leading the Center for Desert Agriculture at King and Billy University of Science and Technology, and one of our main themes is to essentially find ways to feed the world without destroying our planet. And this is a huge problem, and again, with 10 billion people expected to be on the planet by 2050, we need to do all we can to develop crops that are sustainable and are grown sustainably and hopefully locally as well. Next slide. Okay, so our team is, we have 10 faculty right now. We from biochemistry all the way to plant breeding. We've just recently added 3 new faculty members onto the team. Monica Hadosevich works on stress granules, primarily in Arabidopsis. Brenda Wolf from the John Innes Center works on speed breeding and breeding in stacks of disease resistance genes into the cereals. And then Jesse Poland, who just joined us from K-State University in the United States, Kansas State University in the United States. He's a renowned plant breeder. And so we're very excited to have him at KAUST. Next slide, please. Okay, so the Center for Desert Agriculture has kind of 5 themes. We do our basic research. We have 3 applied research projects, one on fast fit palms, led by Ikram, Neo-Domestication. This is a project led by Simon Kratzinger, and the Native Genome project being led by myself. We're also promoting trying to promote a paradigm shift in the Kingdom of Saudi Arabia to move to more controlled environmental agriculture settings. It's what I say about Saudi Arabia, it's hotter than hell and there's no water. So how do we, again, grow crops in an environment like that? And we're thinking that controlled environmental ag will be one of the key solutions for Saudis to grow high-value crops locally and then import some of the staples. We also have an education and outreach program that I won't get into today, and some entrepreneurial spin-offs. And you'll be hearing from Mark Tester later on in the talk in this session about some of those aspects of the Center for Desert Agriculture. Okay, so my lab at KAUST and at Arizona has 3 foci. One is the International Horizon Map Alignment Project. This is a project that we've been involved in for many years, and this is to try to understand the not only the cultivated species of Ariza, which is cultivated rice, Asian and African rice, but also their wild relatives. We're developing a digital gene bank for crops and their wild relatives through sequencing. We have a project on neo-domestication of rice and the wild relatives of rice, and also finally the Kingdom of Saudi Arabia Native Genome Project. And I'm going to touch on these 2 during my talk. Next slide. Okay, so today's topic is about neo-domestication, and essentially what that is could be simply defined as the conversion of a crop wild relative or other potentially economically important wild plants into sustainable commodities. And the idea here is that an example is rather than taking a rice plant and trying to have it grow in salt water, maybe there's a relative of rice that can actually grow in salt water, and then we domesticate it. And I'll tell you a story about that in a few seconds. So this is an example from Zach Lippman's paper on when he essentially neo-domesticated a wild tomato or a wild species of Lycopersicon and domesticated this into more of a food crop, and essentially using gene editing. So this would be to trait introduction of making the plant more compact plant architecture, and synchronizing fruit ripening, which is the SP gene, day length insensitivity, enlarged fruit size, and increased vitamin C. So you can essentially identify these particular genes in this plant and use gene editing to make more of a domesticated plant. So this plant can essentially survive more extreme environments. And now we have a tomato plant that can also produce tomatoes, is more domesticated, has more of a self-pruning habit, and but it can also grow in more stressful conditions. Next slide. So the wild relatives of rice essentially have a large reservoir of genes that could be used for crop improvement, and can be targets for neo-domestication. Next slide. Here is a photograph of some of the wild relatives of rice. This is cultivated Asian and African rice. This is Rufa pogon, the progenitor of cultivated Asian rice, and you can see quite a bit of morphological difference. This Alta plant actually looks quite a bit like a maize plant. So what we say are that the wild Oryza species are agronomically inferior, but contain a virtually untapped reservoir of genetic variation that could be used for crop improvement. It could also be targets for neo-domestication. Next slide. Next slide, please. Okay, so the genus Oryza has 27 species. Next slide. Wide distribution and habitat. You can find wild relatives on throughout the world. Normally, kind of along the equator in Asia and Australia, Africa, and Central and South America. Next slide. We have 11 distinct genome types, which go from the AA, which is the primary gene pool for improving cultivated rice, all the way down to the GG here. We also have several polyploid species as well. And next slide. And even within this, the genus, we have a 3.6 genome size variation. So the nice thing about rice is that, and its wild relatives, or the genomes are relatively simple in terms of their size. Cultivated rice is about 300 to 400 megabases, and if that would be in comparison to the maize genome, which is about 3 billion bases or 3 gigs. The wheat genome is 15 gigs. So the largest genome that we have here is 1.3 gigs. Next slide. So Kishore Jena, who used to be at Erie, he did a study on salt tolerance in rice, and he had a parameter called determination of days of seedling survival, And essentially he looked at many of the wild relatives of rice and categorized them into highly sensitive, moderately tolerant, tolerant, and highly tolerant. And he identified essentially 3 wild relatives that can be considered to be highly tolerant. And this would be in 240 millimolar sodium chloride. And the order of plants that were considered to be tolerant would be Oryza cortata, Alta, latifolia, and grandiglunus. And next slide. So those three of those plants are essentially from South America. Oryza alta, grandiglunus, and latifolia. They're polyploid. They have the CCDD genomes, and you can see their geographical range along here. Many of them are kind of along the Amazon, but it's they appear to be fairly salt tolerant. Next slide. So we did a collaboration with Jian Li's group in China and did a neo-domestication experiment on Oryza alta. We published this in February this year. And the idea here was you essentially develop the way you do this neo-domestication process is to, excuse me, you first try to identify an accession that is that you can transform. Once you've identified that, then you would generate a high-quality genome assembly, and then you would identify homologs of agriculturally important genes from diploid rice, and you find those in the wild species, and then you target them using gene editing. Okay. And the nice thing about this system is that rice was the first crop to be sequenced, and and it's one of the most important food crops in the world. So there has been a lot of studies on how this plant was domesticated and the genes that are important for crop improvement, for grain quality, yield, so on and so forth. So and like shattering, and so since we have all that knowledge, we can take a wild relative, which is very closely related, and through homology, gene homology, modify those homologous genes in that wild species and neo-domesticate that crop. Next slide. Now, okay, so the other plant was Oryza cortata that was highly tolerant. Next slide. Turns out that Oryza cortata actually is considered a halophyte. This is a flowering species here. What it looks like, in the green, out in the shade house. Next slide. It has a biological range from Myanmar to Pakistan. Next slide. This shows it can actually survive the diurnal tides. This is the tide going out. The plants here are close up here, and Oryza cortata has salt hairs on the leaf adaxial and abaxial surface. This is what the seed looks like. These are 2 rice plants, cultivated Asian plants here. This is Oryza cortata here, so it's about the same size. And next slide. It's actually a perennial crop, and it's actually harvested in Bangladesh as a sweet winter rice. It's a delicacy. It's called uridon. So it's a wild relative. Again, it drops its seeds. It shatters. So this is a target for neo-domestication in the Center for Desert Agriculture. Next slide. So we've already essentially generated a very high-quality genome for this species, this polyploid, and we are now in the process of collecting voucher specimens along its species range to determine its population structure. We are working to develop a transformation system in this species. We're studying the functional genomics of its salt tolerance, and we're targeting this for neo-domestication. So the species that we have in hand is very recalcitrant towards transformation, so we are trying to develop a transformation system in some of its other populations from around its biological range. Next slide. So we were talking about native plants, and I just wanted to briefly mention that we've started a project called the Native Genome Project. Next slide. And the goal of this project is to sequence all aquatic and terrestrial life forms that are native to the Kingdom of Saudi Arabia. And this is for conservation and biodiversity, environmental monitoring and protection, evolutionary analysis, and possibly neo-domestication. Here we have the ajwa date palm here, the sawi rice, the falcon. Next slide. So we have a pilot project with the Ministry of the Environment, Water, and Agriculture to sequence some threatened species, rangeland species, and forest species. So by having this basic knowledge of these genomes, it will be possible to use some of that information to improve these plants so they can survive in this hotter and extreme environment. But these are already native species, so they've been around for a long time. So we're hoping that and they can survive in this environment. So we're hoping that we can use this Native Genome Project to help us promote more, identify more plants for neo-domestication. So with that, I'll just close and just say our work and my work is essentially there's going to be we'll have 10 billion people on the planet by 2050. Next slide. I mean, this is next slide, please. Okay, and our big question is, how can we grow enough food to feed the world in less than 40 years? And put a different way is, how can we feed our world without destroying our planet? So we hope that this neo-domestication project will really help us find alternative and develop alternative crops to grow in saltwater environments. So with that, I'm going to thank my team at Arizona, as well as KAUST and funding. And next slide. And just say thank you very much for your kind attention and for, again, inviting me to speak today.
Dr. Rhodes, for this presentation, and I'm happy to see that there are many plant species from our wild environment will be involved in your projects in KAUST, and I think you will find there are a lot of species that fit the criteria that you look for it for saline or for drought-tolerant plant species. Thank you for sharing with us your thought and contribution of Center for Desert Agriculture to explore the potential to change the face of agriculture in the Kingdom of Saudi Arabia by Neo-Domestication or developing high-yielding and stress-tolerant cultivars crop using the crop wild relatives. I think this is a good direction for research to develop some plant species adapted to our environment. And sorry, Dr. Rod, for keeping awake until now. I think this is out of our hand. We thought that you are still in Jeddah or in Thawal, and you are enjoying our wonderful weather. Thank you, Dr. Rod, for your presentation. Now, we are moving to our next speaker, Dr. Abid Hussein, to present enablers to unlock the potential of seawater farming in the Kingdom of Saudi Arabia. He is the member of our scientific team for saline agriculture and innovative technologies suitable for Kingdom of Saudi Arabia, involved with Quinoa, Kingfisher University, KAUST, and KAUST. and he has wide scientific experience working in Pakistan, China, and now in the 10 years in Saudi Arabia. He is affiliated with Kingfisher University since 2011 and also providing consultancy to the Ministry of Environment, Water and Agriculture. Dr. Abid, you have 10 minutes to present your expert opinion in this regard. The mic is yours, Dr. Abid.
Thank you so much. Thank you so much, Dr. Suleiman. I appreciate the opportunity to be part of this virtual event. So, thank you so much, Dr. Suleiman. I appreciate the opportunity to be part of this virtual event. So, the slides to come, I am going to present some of the reflections of scientific research and some of the local experiences and ultimately the international success stories. And then finally, and eventually the integration and of different components and innovations of the seawater farming for better implementation and scaling of seawater farming much needed from Saudi Arabia. That could be the solution for our future in the context of climate change. So, because all of us are well aware about the rise in global temperature, seawater rise, and also these are affecting in terms of sustainability. So here I would like to put some projections from some international organizations. So if the business as usual, so in the growth, so there will be a decline in food. There will be a 56% food shortfall between the amount of food what we are producing now and the amount of food to feed the 10 billion people of the world in 2050. And also the secondly, 593 billion lands of gap of land. And thirdly, of course, there will be a burden of greenhouse gas emission that will be 11 gigatons. So unfortunately, as a matter of currently food producing pockets, although they are underdeveloped and the populations are undernourished. So, but in the decades to come, like 2080, so their productivity will be reduced up to 2080, up to 25%. So furthermore, the depleting water resources also adding more pressure. So and also the region in which we are living, like Saudi Arabia and the Middle East. So all of them, all the countries, they are categorized as extremely high water stress countries. And finally, because of all these factors, our regional food security and but also and many other countries of Asia and Africa, they will have a food sustainability risk. So by keeping into consideration the future predictions and projections, so it is the right time to explore and invest on the R&D of seawater farming, because in our region, all the countries, smaller are bigger to some extent, they are blessed with the opportunity of open seawater. So that could be utilized to develop a seawater farming to contribute to our food system. So, but in this case, the main problem is the main challenge is the salinity. So one of the solution for the salinity might be in future, that will be the, and still people are working on this, is the desalinization. So although if you see in 1970 until now, there is advancement. So in terms of number of desalinized plants, they are increased, and also the capacity, which is now almost 97 million cubic meter per day. So the capacity also, and also you can see in the graph, so most of the desalinized plants are in the Middle East. They are about 39%. But the main problem in this regard is the challenge is the desalinization about the cost. So you can see here, over the period of time, brackish water cost reduced to some extent, but in case of seawater, we need to have the technology, the innovation to make it affordable and to our so that we can utilize it for the purpose of, because now we are completely using this just for domestic purpose. So I think future with technology, reduce the price can be utilized for agriculture. So in the next slide to come, I would like to brainstorm some of the key principles for better implementation and upscaling of seawater farming. So the first the most important, I think it's important to redefine the available impact areas, because in fact we need to define, we need to find, we want seawater farming for which purpose. Whether our purpose is food security, so if we want to go for food security, we need to grow the staple crops. Okay, if you want to go for the biodiversity protection, so we need to focus on some of the plants like the mangrove, and the thirdly, we can also generate opportunity for to support the other systems, like I think in our panel we also have Dr. Mark. I think he will also explain that they are doing a wonderful job using the seawater as for the cooling purpose. And the last, of course, is the most important, market potential. So what is the value of the seawater farming market? But all these things need an investment. So investment in terms of research and development, so that they can develop a technology, and also they can transfer the technology, and so the technology for the adaptation to our local conditions. And of course, needs a partnership in terms of it can be a public-private partnership or some other ways to basically to tackle the challenges of the salinity, the land, and the food gap, and also the climate change, and lastly the cost. So the second is here I will share with you the local research findings, which are actually just first I will present here the Bihar flying agriculture, what they have done in the 90s, and the second, Professor University, they did a wonderful job in this regard. So in case of Bihar, actually this is the project in 1990 they have started in Saudi Arabia using the seawater farming, but with the purpose of growing the crops by oil for high protein, but unfortunately they have to stop the project in early 2000 because of a number of reasons. So because of economic viability and some technical issues, I will explain in the slides to come. So the second is I'm highly thankful for Dr. Suleiman. His team, actually they have done a wonderful job in this regard. They have done about the seawater farming, so what are the potential and opportunities. So I'm presenting their findings there. So they have evaluated the halophytes of the growing naturally under Saudi Arabia conditions. So one by one I will explain all these things. The first, they have screened the wild vegetation of the eastern province of the Saudi Arabia, in which they have come to there are about 45 different species of the plants they have screened, belongs to different, some of them they were the perennials and some of them annual crops, and also all of them they were belongs to about 18 different families, and they have listed about 222 sites. And here, although they have done a lot of things in this project, but I will explain here some important. For example, the salinity tolerance, when they have in the natural conditions they have seen, so you can see here in this graph, the upper shaded region, you can say they are highly tolerant. So their EC in terms of electric conductivity in the soil, then they have recorded that was much more higher. For example, so the fructicosa, you can see here is the much more higher than the level of the what we have in the sea, about 35,000, but here is more than double. So in the bottom species, you can see the EC, although I think most of the plants in the bottom, they were the 0.5, they are dry tolerant. So the third, they have also screened some, they have taken all the plants, and then after that they germinated in their own plots and research experimental areas, and then they have recorded germination by using different levels of the seawater. So you can see all of the species, and they have the problem of the germination to some extent, and also different species they have different patterns, and some of the species they are tolerant to all levels, but most of the species they could not up to high level. So there is a need to have the germination, high germination, because this is the key for any crop to develop. And the fourth, and ultimately, if low germination, then definitely have some in the yield also low. So you can see some of the species they have very little, and some of them they have the middle. So by keeping all these things, yes. So by keeping in mind all these things, the rationale that I think the most important in this regard regard is the crop improvement. So actually these are the wild plants. So we need to have a system to develop these wild plants to convert into a crop. So normally these programs are basically for hygiene, for productivity, better disease, for abiotic stresses. But I think the focus should have like this one, to develop an integrated holistic approach in which genomics definitely, like Dr. Rod, he explained the new genome new domestication. I think they are doing a very nice job to have the domestication and genomics about the wild plants, and then after that backed by the physiological mechanism, and ultimately leading to provide a solution to the farmers. So here I would also want to make the Bihar just now, which I have explained, that they have to stop. Actually, they have a problem in a number of ways. Like they are the wild plants, they were cross-pollinated. So that's why they have the variations. And secondly, the crop maturity is also a very important factor. But for example, if you have 30% of your plants, their maturity level is not up to the level. So that's why they cannot harvest there. So that's why they are not economically viable. So that's why the uniform maturity and also the wild plant and also stabilizing the growth. So these are the things that needs an integrated holistic approach to have a good crop improvement program. In case of international success stories, so there are so many stories, but here I just want to highlight the three different, like one, the Manazar project that was 2001, that was excellent, and by this project they have grown about 1 million mangrove trees plantation for the purpose of number of from the value or from other things. The second Centroform, which is for the food security point of view, using the desalinized water using solar power, and also they have grown about 17,000 tons of tomatoes. And lastly, the Sahara project, which is the purpose of vegetable production and also used for the electricity generation. So, and finally, I would like to, as you know, the seawater farming is an evolving and complex system with various dimensions. So if we want to scale innovation, so we need to have it in a systematic way. So by developing a framework for scaling the systematic innovation, so rather than component innovation, I mean to say that the innovation related to one component of farming seems to be not contributing. So therefore, developing framework to integrate the innovations and combined technologies under enabling policies would help to accelerate and scale up seawater farming as a solution to contribute in the struggle against global challenges. So with this, I would like to conclude that allocation of budgets, investment on R&D, partnership and capacity building are the key drivers to develop seawater farming as a practical and economically viable solution that could contribute to the sustainability of our current and future food system in the context of climate change and emerging food demands. Thank you so much.
Dr. Abid for the presentation and to give us highlight about two case studies done in Saudi Arabia, and I think and part of all the two studies have a relation with Kingfisher University. The one with Bihar, I think it was Kingfisher University involved as a consultant in part of the project. Unfortunately, is not continue, but there are we have seen the tip of salicornia as in the market and in supermarket as additive to a five-star hotel salad, as a bio salt for the salad. So I think there are still also the oil is very edible and very good quality, and the residual of the salicornia could be used as source for feeding animal to supplement nutrients to the case in a small portion. The others, I think, we may discuss it later on. I now will move to invite our next speaker, Dionysia Lera, for 10 minutes about the development of value-added food products in saline agriculture contexts, case studies in UAE and Egypt. And she is working as a halophite agronomist at the International Center for Biosaline Agriculture, ICBA, in Dubai, United Arab Emirates, since 2013. She has been working in evaluating halophytic germplasm both in inland and coastal desert area, and the modular farming system that integrate agriculture with aquaculture utilizing low quality water resources to grow halophytes. Dr. Lera, your mic is now open for 10 minutes. Please go ahead.
Okay, thank you so much for the introduction. And of course, first of all, you can hear me well. You can see my screen, right?
Yes, yes.
Okay, thank you. So thank you for the invitation, and I'm really pleased to share the experience that we have accumulated and compiled so far for the last 5 to 6 years about halophytes, and specifically Salinity and the Quinoa, focusing apart from the agronomic aspects of these two crops on the value chain side as well. So I think I have to click. Okay. So the previous speakers already highlighted some of the vexing challenges that we, the humans, we are actually facing, like the overpopulation, the climate crisis, the biodiversity loss, and recently we had this health crisis imposed by the pandemic and COVID-19. So under these kind of challenges that are currently taking place and probably more to come, it's becoming more and more pressing to take a decision in order to transform the food systems for good, since the business as usual approaches on agriculture seeing that we have to revisit them, and in some cases we have to update them, and probably some of them should be totally cancelled. So what are the, let's say, approaches or trends or different kind of, let's say, tendencies and ideas that are placed on the table and on board to think about how we are going to transform to transform the agriculture in the environments that we are living in, and specifically in desert areas that are really struggling for the local food production, considering even the climate change and the climatic conditions that are really harsh and difficult to control. So sustainable farming systems that combine, that also embed in the concept the environment, but without compromising with profitability and productivity of the systems, are very much, we should focus very much on such kind of approach. Circular economy and circular agriculture by utilizing the outputs of one production component as inputs for the second production component, minimizing the impact on the environment, is one other concept that is becoming more and more frequently faced and brought to the discussions on high level. In addition, it's to increase also the crop diversity and the diversification of the crops within the farming systems. And definitely we have the valuable tools like the artificial intelligence and information technologies that could really facilitate and improve the effectiveness of, let's say, these updated and transformed food systems. But genomics, no doubt, this field has done amazing progress, especially in the last decade. So definitely this is a tool. The previous speaker, Dr. O, talked about the Neo-Domestication of wild plants. So this is a really valuable tool to create such kind of more improved germplasm varieties out of these wild plants. And definitely we have to consider that such kind of approaches should be applied in a more multidisciplinary approach. Sorry, but there is a kind of delay from my end. In a multidisciplinary approach, bringing different experts on board to discuss all these vaccine challenges. Also, especially what it has been severely, let's say, imposed by the pandemic is, especially with the strict lockdowns, was about the how we can increase the local food production. The citizen participation is very vital, especially when we are considering that there should be a change in the. Apologies for this, but there is a kind of, So especially when we're considering that the eating habits of the consumers and the dietary patterns should change or should become more resilient in terms of the local food production and based on what it can be locally produced. And this is also aligned with the new food trends that are, in the discussion or already be introduced in some countries, for example, like algae, different types of mushrooms, insects even are becoming more and more popular and widely embedded in our dietary kind of habits. So all these changes and all these approaches are now becoming more and more popular that to some extent should be embedded in a saline farming context. When we are actually talking about transforming the food system in a desert environment where already salinity issues are prevalent and in some cases they are even further increasing exactly because of the climate change impact. So considering the increasing soil and water salinity in a desert environment, there has been a review paper on desalination and the reject brine that's coming out of it, which is a byproduct, the hypersaline concentrate. And actually 70% of this reject brine is produced in the Middle East and North Africa region. So when we're talking about locally produced food, we have to focus on whatever available resources, water resources, and even unproductive lands are available in order to produce food. When we are considering a hot and dry region like Middle East and North Africa and even beyond that, what we have on our hands to utilize as water resources are exactly seawater, saline groundwater, and even the reject brine from desalination. So this is where actually for the last 5 years we've been focusing on utilizing the reject brine from inland desalination units and in this circular kind of farming approach. So we are desalinating the saline groundwater and the byproduct, the reject brine is utilized to grow the fish. And the waste from the fish, the nutrients, are utilized as natural fertilizer for halophytic forages, salicornia, and other halophytes. You see that the starting salinity of the feeding water is 15,000 ppm. So the reject brine salinity is approximately 25,000 ppm. So we are already talking about really high salinities for this kind of intervention, farming intervention. So a few years later, we decided to move forward with developing the value chain development for Salicornia-based products. So we introduced the previous model, this integrated modular farming in 8 farms in UAE, where we grew Salicornia, and actually we also farmed tilapia fish, utilizing exactly their waste. We had esteemed partners on board and consultants as well. The preliminary outcomes of this project is actually they are included in this chapter. You see here the link for further information. So just to give you an idea, the range of the water in the farms that was used, the reject brine, ranged between 13 and 25,000 ppm, which was really high, and the yield out of these farms, approximately the surface area of all these 8 farms was half hectare. So we got the fresh tips of Salicornia around half ton as well. I have to highlight here that as you see in the photo, the harvest of Salicornia was done manually, and unfortunately it coincided with the strictest lockdowns in Abu Dhabi Emirate, because actually these 8 farms are located in Abu Dhabi. So that meant that we had really limited time where we could actually went to the field and harvest the fresh tips. However, out of this process, we learned and we accumulated very important experience regarding the improvement later on and the challenges that are in place when actually transferring a pilot project from the experimental station to actual farming conditions. So the nutritional profile at different growth stages of Salicornia, in order to explore what is the best stage or what are the best stages of Salicornia, vegetative ones that really suit in different food products. This is a study that we are currently following up with a professor on nutrition on board. Then we had chefs invited for this project, where they created, you see, different range of products from sweet, salty, solid, liquid, even food products, juices, whatever you can think about. The truth is that Salicornia has, and based on personal experience as well, has an amazing culinary, let's say, versatility and flexibility as well as ingredient to use. So this is what we had also identified with our chefs who worked on board for this project. We still went one step further. So we collaborated with a food company, and actually the food company, by having this intermediate scaling up and business model in place, we wanted them actually to have such kind of preliminary version of the product introduced in the market. So currently, they are purchasing the Salicornia from the farmers, trying to establish in a more solid way the sustainable business model of Salicornia in UAE. And they are actually including Salicornia as ingredient in their burgers. And you can see that this Salicornia burger is already sold in the market, so whoever is actually visiting UAE can visit Union Coop, these hypermarkets, and can purchase the Salicornia burger. One step more, I should say, that the team decided to move ahead with this activity is the Hello Kitty Kitchen Lab program that takes place since 2019. However, still some activities were hampered exactly because of the COVID. However, now we are in very much full action for this program. So we are actually raising awareness to the consumers in UAE about halophytes, about desert farming. They are actually cooking on the spot with a chef different kind of recipes, having quinoa, salicornia as ingredients. And in addition, they are learning about the, what kind of products and crops can be locally produced, creating this more sustainable consumer mindset that is really needed nowadays for farming and for agriculture overall. So similarly, and similar kind of approaches were adopted for a project funded by HSBC Bank in collaboration with ICBA in New Valley in Egypt, where actually quinoa varieties were evaluated and different kind of products in collaboration with the local women and youth of the region were actually embedded in this kind of initiative, in these project activities. Similarly, so you see different kind of products. I would like also to highlight here that we are focusing on embedding these different crops, these unconventional crops, to the local eating patterns, to the local diets as well. Not only for quinoa, but of course for salicornia. So you see different kind of recipes which are more, let's say, Egyptian based or Arab based, I should say. So different kind of, products were created. So similarly, community events took place, social events, because these somehow, in order to convince the farmers, the communities, and when that there is a potential of a business model there, we have to convince that this, they have actually to touch, to feel the products. So we have to create this kind of feeling and emotion to them that, such kind of product or such kind of approach is feasible. Similar approach, and actually my colleague who happens to also join the workshop today, Dr. Hirish Aziz, also took over this in Morocco with similar approach. And if someone or if some of you have the questions, okay, but there are no challenges that you faced, definitely there are challenges. So this is why we are focusing more on breeding aspects of quinoa and salicornia, because the uniformity of characteristics of the crops is really vital to have a steady and a solid kind of yield. Now the challenge, especially in UAE, and frankly speaking, after all this awareness and after this project taking place, we are receiving more requests, the ICBA, the farmers as well, about having salicornia production throughout the year. And you know very well that salicornia is a seasonal plant, especially the vegetative stage is just for 2-3 months and maximum, especially in this environment, in a hot and arid area. So having now salicornia or quinoa growing, especially salicornia, since it's used for the fresh dips all year round, is the next challenge for us. Probably using a container or an indoor kind of approach, an indoor protected system. The next challenge is the improvement of the mechanization processes for quinoa and salicornia. Specifically for salicornia, I should say that I mentioned that we did the harvest manually. However, of course, if there is a kind of machine in place adapted to the local conditions, that would much facilitate the yield and would increase both productivity and profitability in the end. Regarding the training of the farmers, because the one extra challenge that we are facing as we are introducing such newly farming approaches, newly crops, is how the farmers can really adopt these kind of technologies and apply the management practices in a proper way. So in collaboration with Smart Labor, with a company in UAE, We developed, especially with the pandemic, we had to convert all the trainings, all the physical trainings online. So this was a kind of a module that was created, a virtual one, translated in 3 different languages. So we have English, Arabic, and Urdu. We have uploaded some training material, and this module gives the ability to the participant to pre-assess his knowledge and then post-assess his knowledge and the information he gets after having access to this training material. So of course this has been implemented last spring and we had great participation specifically for some sections like the value chain, like the Halophyte's marketing potential, like the management practices. However, exactly because the application of such systems need further improvement, it's still under a pilot phase. So my concluding point is that the more checkpoints we have from this list of approaches and new trends and directions, and in some cases, these are imposed directions, I think the more solid food systems we can create for now and for the future. My last slide refers to this WASAG, the Global Framework on Water Scarcity in Agriculture. It's under the auspices of FAO. Some esteemed speakers are already part of this framework overall and of the Saline Agriculture Working Group. So whoever is interested, we run regular meetings and sessions from time to time. So whoever is interested actually to join the team, the group, we run different activities and tasks and assignments, is most welcome. So you can contact me directly or Arjen from Arjen de Vos, who is already on board. I just saw his name. So please feel free to touch base with us. That is all from my side. Thank you once more for your participation and for the invitation. Thank you.
Okay, thank you, Dr. Lera, for this presentation and your thought regarding quinoa and saliconia and this valuable information and also delicious products that you are showing to us. Now I will go to our next speaker in this session, Dr. Nadia Bezizina. She is the Mary Croy Fellow, University of Tasmania, Australia. Dr. Nadia is affiliated with the University of Florence, Italy now. I am inviting her to speak about 10 minutes, please, on going underground, understanding how roots drive plant responses to heterogeneous salinities. So please, Dr. Nadia, the mic is the floor, and I will appreciate that you limited your presentation in 10 minutes, please.
Hi, everyone. So, I guess, can you see me? I'm not too sure. Can I manage the slides myself? So I guess, so today this is I'm a plant physiologist and I work on halophytes, but today I'll really be talking about some reflections I made in the past 10 years and regarding the fact that saline soil are really not uniform, so they're highly heterogeneous in time. And next slide, please. So again, so here I'm just not probably going to talk much about is the fact that the extent of the salinity worldwide and the fact that climate change is really worsening the salinity. So next slide. Again, sorry. So I have a few. So generally, how do we address the problem of salinity? And as already you have introduced, is that so you can either manage saline soil, or there's also the approach of the breeding. So, and that generally, the fact the breeding approach is usually done through doing experiment under uniform conditions. And the big question really that what I noticed when I went out in the field is the patchiness of saline soil, and which really reflects the fact that salinity in the soil is highly heterogeneous. Next slide, please. So going back into more than 20 years ago, and there's this old study that was done in the seashore in the Dead Sea, which I think has been quite overlooked, but I believe is a fundamental study because so what they observed some halophytes growing in a highly saline, hypersaline environment in soils with salinity running 3 to 4 times seawater, and what they asked themselves is how is that possible? And the study really highlighted the fact that these halophytes were able to use these occasional floodwaters that had a much lower salinity, and they used that to survive in these extreme environments. So, next slide, please. So going to, so I then asked, okay, let's go and have a deeper look at the soil salinity. Next slide, please. Again, sorry, thanks. So here is some work. So I went in the literature and looked at some studies that have been done here in Italy, in wetlands. So, and these are naturally saline environments. And on the other side, you can see some old man salt bush growing in Western Australia. So these studies went and looked at how salinity changes in spaces in this soil. And as you can see here, next slide, please. The salinity really changes quite substantially, and it goes from a couple of decisiemens per meters to up to 4 times seawater. And within the rooting zone, for instance, if you're talking about old man salt bush, which has quite an extensive root zone, the salinity varies from a few orders of magnitude. And one thing that is fundamental to consider when talking about the heterogeneity of saline soil is that it's not just the salt, but also the water. So it's the combination of both. And for instance, in Mediterranean environments, the final drought really is the factor that exacerbates the problem of salinity. And that will exacerbate the heterogeneity in the soils. Next slide, please. And this heterogeneity is not only in space, but also in time, as you can see here in this transect, again, that were taken in the wheat belt in Western Australia. Again, as you can see, the salinities in the soil solution goes from less than 5 decisiemens per meter up to 180. So it goes to more than twice the seawater. And so the plant is subjected to these extreme changes in soil salinity. And next slide, please. So in these slides, I've shown you examples of the heterogeneity in naturally saline environment and rain-fed system. But the thing is that heterogeneity is also the norm in irrigated conditions. So here, and that was something that was quite clear already in the first studies done in UC Davis in the 1950s. So that salinity, with irrigation, you have the wetting front, and then you have salinity accumulating at the edges of that wetting front. And the heterogeneities will change depending on the climatic condition, irrigation schedule, and plant activity. So it's a fundamental aspects on saline lands that we do have to take into account, mostly for the breeding and the managing of saline soils. Next slide, please. And so here I'm going to briefly show you a study that I made, so that I will to show you I asked myself, how do plants integrate this heterogeneity? So usually when looking at plant tolerance, we just, by looking at uniform condition, we see specific responses, but then what does happen when we put in the heterogeneity? And so I worked, next slide please, I worked with, again, I have a few, and again, yes. So I worked with Astriplex, the Old Man Saltbush, because, so I did this work in Australia, and that is really used quite extensively for revegetation, but it also has an extensive root system, which is more likely to be subjected to spatial changes in soil salinity, and is a perennial species. So again, subjected to temporal changes in soil salinity. So I conducted, next slide please, I conducted this experiment again, thanks, and again, so I had quite a few. So I conducted this experiment using cuttings of Astriplex, and I did some split root experiments where I had the low salt side and a high salt side. Next slide, please. And so here I'm just going to show you a quick, again, next slide, a couple of slides. You can go ahead with a couple, yes. So here you can see that I did this experiment where I exposed plants to 10 millimolar in the low salt side and 3 times seawater, a bit mimicking the I guess, the variability that I've seen in the literature. And yes, you can see that in that case, when you have this extreme heterogeneity, really the growth of the plant was similar to that of the low salinity. So I used the uniform 10 millimolar sodium chloride because being a halophyte, it did require some salt. And as you can see, the factor describing the plant growth was the low salinity, and the plant was not affected by the fact that half of the roots zone at the beginning was exposed to extreme salinities. Next slide, please. And so I then did another study where my question was like, what does drive plant responses under heterogeneous salinities? Because I had this study that really showed that the low salt side was the main factor driving plant growth. So I did some hydroponic experiments, still with these split root setups. Next slide, please. And where I had different, in this case, I used a wider range of salinities, and that went from 10 to 670 millimolar sodium chloride, so a bit more than seawater. And then I had the heterogeneous salinity, where I had, in the high salt side, I always kept the 670 millimolar sodium chloride, whereas in the low salt side, I went from 10 to 450 millimolar sodium chloride. Next slide, please. And so here I'm going to show you the results. So these were the results observed. So I'm just, because of the time constraint, just going to show you a couple of results and then go ahead. So really here, shoot elongation, and so this is the elongation on the uniform salinity, and being a halophyte, you almost had, there was a growth, there was a growth stimulation with up to 220, but then there was only some penalties once the salinity went above 450 millimolar sodium chloride. But then, so under heterogeneous conditions, so when half of the root zone was, we had 630 millimolar sodium chloride. So if you can please go to the next curve, you can go, yes. So as you can see here, the fact that half of the root zone was exposed to high salinity did affect the plant growth. So unlike the other example where I had the extreme salinity, in this case, the fact that half of the root zone was exposed to this high salinity led to a significant decline in shoot elongation. However, and therefore, the lowest salinity wasn't anymore the parameter, the best descriptor of shoot elongation. Next slide, please. But in this case, what I noticed was that if I plotted the data against the mean salinity in the root zone, so that really was a better descriptor of shoot elongation, which would suggest that for this parameter, the plant integrates both salinities in their root zone. Next slide, please. And so yes, and another one again. Sorry. So here is the fact that stomatal conductance again. I measured and looked at stomatal conductance. As for shoot elongation under uniform condition, there was no significant penalties, only about 450 millimolar sodium chloride. However, having that one root half at high salinity led to significant declines in stomatal conductance. And also in this case, the low salinity in the root zone wasn't the best descriptor of the plant response. But as you can see in the next slides, again, so that was the mean salinity that was the best descriptors of the plant response. So I went on and looked at sodium, leaf sodium content, that increased with uniform salinities, but then again, having that, the fact that part of the roots were a high salinity led to significant, some increase, not that greater of increase in leaf sodium, but also in this case it was the average root zone salinity. So if you see the next slides, it was the mean salinity in the root zone that was the best descriptor of the plant responses. The only exception, as you will see in the next slides, the only exception to this was the midday shoot water potential. Well, so both midday and pre-dawn, so the measurements of the water potential that really indicates where the plants take up most of the water, and it will equilibrate with the lowest salinity in the root zone, which also would suggest that under heterogeneous condition, really hydraulic signal might not be the most important factor affecting shoot physiology, but probably it's important to be looking at phytohormones. And then yes, again here that confirms that the mean salinity in this case wasn't the best descriptor of plant responses. And and if you go here, I had for a couple of slides. So if you go back to the teaser where we had please go ahead. And again, just yes. So how do we incorporate the results where I showed you initially where I had that extreme salinity in one root half, and in that case it was the least saline area of the root zone that really drove plant physiology. And so if I go again and show you, I plotted the data against again the lowest salinity. And as you can see here, the mean salinity is not the best descriptor in this case because the data under extreme salinity really stand out. But under this condition, what I observed was that if you see in the next slides, so what really happened here, so by putting a salinity that completely inhibited plant growth, then the plant responded by foraging, by not proliferating in the low salt side. And there was a compensatory increase in root growth in that side, which was even greater than the growth observed under uniform low salinity. And that led to a preferential water uptake from the low saline side, which really then explains, so if you go please, the next, again, another slide. So why it's important to take into account the root activity and the root, I guess, where the root grows. And so meanwhile under heterogeneity, when I had smaller salinity or lower salinity range, so only 670 millimolar, being these are halophytes that really did not inhibit root growth in that side. So I did not observe this compensatory root growth on the low salt side. And that really showed that.
Nadia, can you please go to the conclusion because you are running out of time?
Keep going, please. Again. One thing that is important to consider under heterogeneous conditions is that there's also the fact that the nutrients are highly heterogeneous in space, and it's not just salt. So if you go ahead, so that really, here I think it's very important. So I have some question that should be taken into account when doing all the breeding and the managing of saline soil is it really, how useful is it to do how much can we transfer of what we know about uniform condition in the field where you actually heterogeneity is the main factor driving plant growth, and then if you add the heterogeneity of nutrients, so how that affects the response. And I think so I've been collaborating with Patrick Brown at UC Davis, and what his data shows is that when you add the nutrients into this, that response really changes. And in terms of irrigation, for instance, how small can that the area that has all the water and nutrients be, maybe you can really reduce. When I use the split root, I use a 50-50%, but maybe perhaps you can go to a smaller percentage of the root system that has a good water, how with nutrients and water, and have saline soil in the, and that would really affect, so how would that affect the plant physiology? And then the last is how do you measure soil in, so it's not, so ECE 1 to 5 and ECE maybe it's not a factor, it's not sufficient. But with that, I would like to thank you and thank the organizers for inviting me. Thank you.
Thank you, Dr. Nadia, for this information and high-level research. And I think the questions have been posted here is need a lot of research, of course, but we may consider something regarding the potassium-sodium antagonistic effects and how potassium or sodium entering the plant, and is it active or passive entering and absorption. In that case, we need to look the energy required for such mechanism in the plant, and this may affect not only the root growth, but maybe it will affect definitely the shoot growth. And if we discover all the aspects related to the energy required in such mechanism, I think we may come to a solution for the growth of the roots and understanding fully the salinity mechanism in such plants. Thank you very much, Dr. Nadia, and we will come to some questions in the discussion session, but it is now, I think we are a lot behind our schedule. I will go to our last speaker in this session is Dr. Kate Nigazi. She is a postdoctoral research at Fiji University, Amsterdam, working on governance for biodiversity and food systems. She also coordinates SALAD project, Saline Agriculture as a strategy to adapt to climate change, which involve 11 partner institutes from 6 countries in Europe and Africa. It addresses the research area of food security under climate change through saline agriculture, aligning Fijian research and the practices among European and African countries, focusing on saline agriculture upscaling. I welcome Dr. Kate to present the potential of saline agriculture upscaling in the next 10 minutes, and also I will appreciate limiting the presentation in 10 minutes. Dr. Kate, the mic is yours.
Thank you very much for the introduction. Can you hear me well? Yeah. Thank you very much. Good morning and good afternoon. Thank you very much for the invitation to this workshop. It's a great pleasure to present here. And today I would like to talk about the potential of saline agriculture upscaling. I will keep my presentation brief due to the time limits, but I hope I can present some sneak peeks into what happens in the North Sea region and also Mediterranean region. So what I'm going to say is first salinization as a global challenge. Then I will briefly go over the location of saline soils, focus mostly on the upscaling strategies in saline agriculture, present 2 examples on the local scale, so the North Sea region and Mediterranean region, and then on the global scale, here mentioning 2 networks working on salinization, and then finish with a way forward and a call to action. Next slide, please. So, starting from the very beginning, salinization is gaining attention also in the press, in media. We can see that it's reaching different directions. It's mentioned in the context of climate change, so SDG 13, in the context of food security, SDG 2, also going into food sustainability and sustainable production, so here SDG 12. But also as an innovation opportunity and in the context of breakthroughs as it comes to both science and practice. And this is what I would like to focus on today and also briefly discuss with you. Next slide, please. When we talk about salinization as a global challenge, there are a few directions. There is, of course, growing freshwater scarcity that was already mentioned by a few panelists. There is the issue of halting biodiversity loss while still maintaining food production for the growing global population. There is, of course, to climate change, which can be related either to the global sea level rise, to increased possibility of flooding, but also to more persistent and longer droughts. And of course, this all boils down to the opportunities and capacities that we have to produce food under saline conditions, which can occur, of course, in the soil, but also in the water. Next slide, please. When we think about the location of saline soils, we have already today seen quite a few maps. This is the map that has been launched, I believe, 3 weeks ago by the Global Soil Partnership. That's been a collaboration of many countries putting together the maps and knowledge about current location of salinized areas. So I very much encourage you to go also to their website and have a closer look. Some areas still need to be mapped, but we can see that they concentrate mostly around Central Asia. Also, well, this is not really visible here, but Middle East and North Africa as well, and some other places around the world. Next slide, please. In context of the location of saline lands, we also think about the upscaling strategies. So we know that salinity occurs, we have to deal with it, we have to live with it. What can we do to actually build on it? We, in our work, focus on the concept of upscaling, which is efficiently increasing the socioeconomic impact from small to a large scale. So moving from a small scale, field experiments, lab experiments, to a larger scale. So, for example, bringing saline products to supermarkets, to restaurants, but also to other countries. So when we talk about upscaling, we can see that there are 3 directions of upscaling. First one is horizontal, so reaching to new countries, and we know that there are countries that have been working on salinity for years and that have exceptional knowledge in this regard. So we try to connect different countries, different expertise located all around the world. There is another type of upscaling, which is vertical upscaling, and here it is meant as going higher on the organizational levels. So it quite often starts with the farmers, farmer associations, vocational training, but then we also want to go higher in terms of institutions. So how does it look at the level of ministries, at the policy level? How does it look also as it comes to impact investors? We then go up and we also scale up as it comes to organizational levels. And the third step of upscaling, we go quickly back to the previous slide, please. It's the diagonal upscaling, and that's the one focusing on new strategies and components. So here we think business-like. Okay, what are the new varieties of salt-tolerant crops? What are the new strategies and practices, for example, soil and water management? What are the innovative components that we can use, marketing strategies, all of that. So we can see that there are different directions where we can go and different ways in which we can approach it. And now I will talk about 2 specific cases. So next slide, please. Yes, first looking at the North Sea region and Mediterranean region. This is the project that have just started this year, SALAD, and it had a predecessor called SALFAR, the one that is basically finishing. Well, actually early next year there will be a final conference summing up the results. SALFAR, the project focusing on the North Sea region, was mostly looking at the field trials, but also market potential. So basing on that, we decided to follow up and to think, okay, now we have that knowledge, how we can scale it up, how we can bring it further. So we decided in the project called SALAD to bring together 2 regions, the region of the North Sea and the region of Mediterranean Sea, and try to exchange common learnings and expertise. The first thing that we arrived at is, of course, that even though we have the common challenge of salinization, there are differentiated conditions. Looking at the climate change, one is more dealing with the sea level rise and the sea seepage, coastal floodings, whereas the other one mostly has a problem with prolonged droughts, also extreme weather events. But what brings them together is the food production, especially food production under saline conditions, also quite often located next to the World Heritage Sites. For example, Wadensee area, which is an area north of the Netherlands, and also Germany, which is very important for migratory diversity. So here comes an issue. Can we produce food there? Can we use this area for work? Our approach in the project focuses on 4 steps. First, we look at soil, water, and plant interactions and the models under which we test different pedoclimatic conditions. Then we focus on production pilots and nutritional characteristics of saline products. So we also check what nutritional values they have. And here we look at 4 crops specifically, crops that are crucial for the countries that we have, and also some of the crops that you've already mentioned today. So we have potatoes, very important for the North Sea region. We have tomato, we have also quinoa, and we have New Zealand spinach as one of the new crops. Further, we look at the stakeholder interactions and community. So here we look at the upscaling in terms of institutional support. We also check how this whole value chain from farmers, associations, retailers, researchers, and also people who look into recycling and post-product management can come together and cooperate to basically strengthen the food system based on the saline production. And finally, we look at the opportunities and barriers for upscaling. So we take a very economic approach, check what are the chances, what we can learn, whether this is economically also a viable option. Next slide, please. Yes, and the second part that I wanted to mention here are the 2 global networks, INSAS and WASAC. Next slide, please. The first one that I wanted to mention is INSAS, so the International Network of Salt-Affected Soils, launched this year and having 4 groups, having together also more than 600 members. The groups focus on mapping, sustainable soil management practices, water, so integrated soil and water management, and crops. So here, halophytes and salt-tolerant crops. This is an open network, so everybody can join one of the working groups, and we also work on very specific deliverables. So here I wanted to also invite everybody to consider joining this network and collaborating under FAO auspices as well. And the second network, so can we go to the next slide, is WASAC. This is the one that Dionysia has already mentioned, so I will just name it briefly. This is the second expert group under the Global Framework on Water, Scarcity and Agriculture, launched a few years ago and also focusing on identifying practical solutions. I believe that Dionysia described it really well, so I won't go here into the details. But what I mean by presenting those 2 networks is basically focusing on the upscaling, also institutionally, and looking more at the interactions and collaboration and cooperation all over the world. So that brings me to the way forward and also looking at 3 aspects of upscaling in this sense. First, diagonal upscaling, so looking at the new components and how we can bring it together from the business and practitioner perspective. And this is identifying and improving salt-tolerant crop varieties, also looking at the sustainable soil and water management practices, and evaluation and innovation across the whole value chain. Here, I want to briefly add that the projects that we work on also very much focus on marketing, on bringing it to the markets, to retail, but also to the restaurants. So we are now also collecting recipes for all the crops that I've mentioned, and it's great to hear presentations that also look into this aspect. Then we have the horizontal aspect, so going broad. Then we go to different countries all around the world. And these are the networks that I have just mentioned, joining together our knowledge related to salinization, but also development of the regional centers, which is very important as well, because quite often, even though the challenge is the same, conditions differ between, for example, North Sea region, Mediterranean region, and also other places in the world. And then finally, we have the last type, so the vertical upscaling, and here going into the supportive land and water use policies, so the policymakers, and talking to this audience and also seeing how they can be addressed. Sometimes there's a specific policy dedicated to salinization, but most often in most countries, these are just bits and pieces included in different policies. For example, water management, biodiversity governance, or soil management as well. And finally, creating and also implementing investment opportunities. As salinization is gaining momentum, this is also the moment to act, to ask global financial organizations and local investors to consider whether they want to invest in a very prospective area that's probably in the next 10, 20 years will gain much more attention and much more potential, so that right now we can start upscaling and preparing for that. With this, I would like to finish my presentation. Thank you very much for your attention and looking forward to the questions.
Thank you. Thank you, Dr. Kate, for this presentation and this thought, I think, and upscaling the saline agriculture, the saline, the halophytes, the crop related to salinity is a good approach. And I think also you are looking to scale it out to another regions and to other maybe farmers will benefit from what you are doing and what you have achieved in these regions. I will go now to the discussion, but I have no time. I just have maybe two questions, one from Dr. Mish'al Mutairi. If you are with us, Dr. Mish'al, you can put your question or ask your question. I think you would like to ask Dr. Rod about something. Dr. Mish'al? I think Dr. Rod, he wrote to us about define the salt tolerance of rice. I don't know what he mean by define the salt tolerance of rice. If there is any achievement, maybe having to define some variety or some species salt tolerance for and what the level. This is the Mish'al Mutairi question. Dr. Rod? Oh, yes.
On mute, sorry about that. Yeah, so I think the question, we already did it through the chat group, but I believe the question was addressed about the Oryza cortata. And the Oryza cortata can grow in full salt, it's found in full salt water. We've done some experiments with Mark Tester at KAUST on this, and our cortata can survive full salt water, and it will flower in maybe 50% salt water, but the optimal flowering right now is in maybe about 25% salt water. But it's normally found in regions that, you have the diurnal tides, but there is some brackish water coming in from rivers and things like that. So that's the normal conditions for cortata. So you're going to need some fresh water around, but that's it.
Yeah, I will go to Yassine Qallab, please, if he's with us. Okay. Yassine Qallab with us. He has a question. Okay, so we will go to Yusuf, please.
Yes, hi, Rod. This is Yusuf from the Seed Center at Quinoa. My question, I have a couple of questions in mind. One regarding the rice, when you mentioned that there is a wild type variety which can tolerate up to 240 millimole. And, so is there any cultivated cultivars that can tolerate and produce economically? That's one of the questions. And the other is for improvement, I think what you mentioned is that you will be using the gene editing or let's say, GMO with transgenic label. I don't know if you're going to do so, but as you know that people globally still debating about the acceptance of these technologies, and in Europe, as you know, that they are still, they don't accept GMO, and even with gene editing in 2018, they even recognize it as a GMO. So, and for consumption and cultivation. So, what's your input on this, please? Thank you.
Thanks for your comments. So I think the first question was about those wild relatives and their salt tolerance. Again, I think right now it's about this the 250 millimolar salt concentration for those species, and then they actually the plants could go to seed. So that's kind of where we are with that. But we're doing some more experiments now on really defining that salt tolerance. And I am not a plant physiologist, so I'm collaborating with Mark Tester on that. The other question about the GMOs and gene editing, so that's that always comes up, and in the U.S. A genetically edited plant is considered not considered GMO, so that is accepted. So I think we can definitely do things in countries that have those types of regulations. I recently visited Genome, and they are writing the laws right now. But my understanding is that they will allow GMOs at Neo. So that would be a site for testing some of these crops, which is actually would be fantastic for not only academic research but also for industry as well.
Thank you, Dr. Rod, for the answering. I think we need to work with ISO regarding defining what belongs to GMO, and if genome editing species is considered as a GMO or not. And I think if we define it very well and come to this high level with ISO, I think we will be able to maybe scaling out and up the genome editing species, which is also a benefit for food security and for the world and globally. Thank you, Dr. Rod, and thank you, Dr. Abid and Dr. Lera and Nadia and Kate for this session, and I'm thankful for all of you for your inputs. And I'm looking for further discussion, but unfortunately the time is very tight for us and it's limited. And I will go now to the second session. And this session we have three keynote speakers. First, I would like to invite Dr. Mark Tester to speak about innovative technologies for developing financially and economically viable food system. Dr. Mark Tester is well-known scientist in the field of molecular genetics, mechanisms that enable certain plants to thrive in suboptimal conditions, like high salinity or high temperature, and then they will deliver the output in economically viable system. He is also the Associate Director, Center for Desert Agriculture, KAUST. His large aspiration is to unlock seawater by developing a new economically viable agricultural system where salt-tolerant crops are irrigated with partially desalinized seawater or brackish groundwater. A company, Red Sea Farm, have been established to facilitate this delivery and benefit over the world in this technology. Now he is with us virtually to give a 10-minute talk about innovative technologies for developing a financially and economically viable food system. The mic is yours, Dr. Mark, and please limit your presentation in 10 minutes. Go ahead, Doctor.
Suleiman, and it's a pleasure to be here. Thank you for asking me to join you. Next slide, please. We're wanting to... Next slide, please. So one context slide only, which I think is very important, is that we're mining groundwater resources significantly for the production of a significant fraction of our food globally, and as those groundwater resources are depleted, so the quality goes down. So we do need to not only be thinking about growing plants with salt water, seawater, but also with brackish water. We also need to minimize our abstraction of this groundwater. Next slide. The minimization of freshwater use is absolutely essential from my perspective, especially living in the Middle East. And to do this, I think there's two options. One is to try to minimize the use in the system of fresh water, such as use increasingly controlled environment agriculture, and or substitute as much fresh water as possible with salt water, such as by the use of salt-tolerant crops, such as we've been seeing in this meeting so far. Next slide. If we're wanting to minimize the use, or substitute as much fresh water as possible, we really do need technologies to help us unlock seawater and other low quality water that we currently cannot use to try to contribute to our food production. Next slide. And one key that we use to unlock is, in fact, it's a pair of keys, if you like. It's a combination of genomics and phenomics. We've got new technologies, and this gives me much hope for the future in this field. Genomics is turbocharging genetics, and hand in glove with the amazing things happening with computer vision, artificial intelligence, Internet of Things. These are all helping us characterize, phenotype the plants much more accurately at much higher throughput. And so this combination of genomics and phenomics gives us huge opportunities for serious innovation in the improvement of crops. In particular, it gives us opportunities to unlock wild germplasm. Next slide, please. We can do two approaches. One is to use wild germplasm to make existing crops more salt tolerant, and we can take another approach, which we've heard described already, where we can get plants which are already very salt tolerant and turn them into crops. I have to admit, I spent most of my career on the first one, but I really think that the second one has got a huge amount of opportunity for generating step changes in our ability to use low quality soils globally. Next slide. So I'm going to focus on this more recent work that we've been starting to do in my laboratory, which is the domestication of salt-tolerant plants. We started this journey with quinoa. Next slide. In quinoa is a plant with good salinity tolerance, good drought tolerance. It really is a crop for marginal lands, such as shown here in the photographs from the Altiplano of Bolivia. The plant really is quite remarkable in its ability to grow in marginal lands. Next slide. But it also is a crop that has huge yield potentials. These are slides, except the bottom left-hand one. The other slides are from field trials we've been doing on the Tibetan Plateau in southwestern China, and the yield potential really is remarkable in some good quality conditions. Next slide, please. It's also a crop that's got very high nutrition, so in many ways it's got lots of opportunities, but it also has many problems and does need still significant genetic improvement. In particular, it does require what we could call a high reliability. It needs to have a greater stability of yield. It needs to have better early vigor It needs to have traits, sort of, I'm working with a paradigm, I guess, from the cereals, where you need to have a plant which is dwarfed and has a very simple habit, rapid growth, rapid production of seeds. It's a dicotyledon, so this excludes many herbicides for management of fields, so it really does need to have herbicide resistance introduced. And David Wu in China has been doing an excellent mutation-based breeding program to introduce herbicide resistance into quinoa. We're doing a bit of work with day length sensitivity as well, but the key thing is its inability, or sensitivity I should say, to grow with high temperatures. And if we're looking at marginal lands which are often dry and saline, really for most of the world you also need to have more heat tolerance. And so that's a major thrust of our work at the moment. We're doing quantitative genetics in the field now. We've got good quality genome sequencing, and we also have been able to resequence the genomes of about 1,000 accessions now to enable us to have to do association genetics, quantitative genetics in the field. Next slide, please. That's giving you a brief introduction. It's all we can do in 10 minutes. Brief introduction to the aims of our work, at least with quinoa. Quinoa's fine, but it only grows in half seawater or less, better less, I have to admit. So if you've got a field and you're using seawater as your ultimate source, half seawater is amazing, but you still need half fresh water, and it's still a large amount of fresh water required for that crop. So I am increasingly now looking at plants which can grow in full seawater. And this is work now led by Vanessa Molino, a research scientist in my laboratory, where Salicornia is able to grow, as you know, in full seawater. Its optimum yields are around about 1/3 seawater, but still a remarkable, very impressive plant. If we go to the next slide, just to introduce the fact that there is fantastic genetic variation in quinoa. We are sequencing the genome and resequencing more accessions to try to do what I introduced to you we were doing in quinoa, but doing this in Salicornia. So as I say, just a brief introduction to a couple of the bits of work we're trying to do. Next slide, please. It's all very well to do the work, but we also need to deliver the research, and often I think we need to pick this up and do this with our own hands. I've tried for many years working with the major companies for delivery of some of our research, and really had very, very little interest. And so I think the work at ICPA is excellent in delivering, I should emphasize actually, and others. ICPA is, I think, a notable intergovernmental body, or independent body actually, sorry. I've decided to also set up a company, because nothing is sustainable if it's not just environmentally sustainable. It also needs to be economically sustainable, economically viable as well. And for this we're focused, at least initially, on covered agricultural systems where we're minimizing the use of water, but also trying to substitute as much fresh water as possible with seawater. And covered agriculture systems are very important, because they also are very good for horticultural crops, which often have high nutrition. So if we look on the next slide, we see that food nutrition is predicted to be really much more important than basic fundamental provision of starch in our foodstuffs. So this analysis from the EAT Commission, the EAT Lancet Commission, published in the Lancet a couple of years ago, predicts that if we're eating they calculate that given global population increases, and if people had a healthier diet rather than eating what they eat, if people had a healthier diet, and if we reduced some of our waste, halved our waste, we actually don't need to grow any more cereals in 2050 than we are already growing. But what we do need to do is grow a lot more fruits and vegetables. And this is very important. And so I've become quite a fan, I must admit, of plant horticulture and the development of fruits and vegetables and systems for growing them. Next slide. So in the little company we've set up, which is growing very rapidly, I should say, we're bringing together plant science and engineering, and of course using IoT and machine learning to develop a greenhouse-based agricultural system where we use about 1/10 of the fresh water that would be used in a normal agricultural system. In the next slide, this is summarized where we have in a normal greenhouse, for a kilogram of tomatoes, you need about 350 litres of fresh water, which is very similar to the freshwater footprint of tomatoes grown in open fields. And that's because although the plants are using less water in the greenhouse, fresh water is being used for the cooling of the greenhouse. Now you can substitute, you can greatly reduce the freshwater footprint by using mechanical cooling. That has a massive cost in terms of energy consumption and usually CO2 emissions. So with our greenhouses where we're cooling, using evaporative cooling, using salt water and different types of salt water, we can both reduce the freshwater footprint and not have any increase in the energy footprint. If anything, in fact, it's a reduced energy footprint. Next slide, please. So the system now, we found that saltwater evaporative cooling is fine, but we actually need to have with it a series of other technologies which can address, so we call this our technology stack, and with this we can address different aspects of life in this type of tough environment that we live in the Middle East. Next slide, and that will be the end, Mr. Chairman. So all we're doing here is just reiterating the importance of reducing freshwater, the overwhelming importance of reducing freshwater use. We can do this by trying to minimize our use of freshwater and, of course, substitute as much as need water to grow plants. That's not negotiable. So just my final two slides are just to thank the people with whom I work. Next slide, please. And thank you as the audience. Thank you.
Okay, thank you, Dr. Mark, for this presentation. And as I mentioned, the aspiration of salt and seawater farming, I think this is a chance now. There are many have been targeting Salicornia, Quinoa as a candidate crops to be domesticated for saline agriculture. So we will go to our next speaker, and we will come back to you, Dr. Mark, in the discussion. Our next speaker is from India, Dr. Barbara Sharma. He is director at Indian Council of Agricultural Research, Central Soil Salinity Research Institute. Dr. Sharma has made significant contributions to the understanding of the physiological mechanism and the salinity stresses in different crops, and was involved in developing salt-tolerant, high-yielding genotypes. He is also the president of the Indian Society of Soil Salinity and Water Quality since 2016. Now, I welcome Dr. Sharma for 10 minutes to share with us Indian experience about the harnessing productivity from salt-affected soil. The mic is yours, Dr. Sharma, and please limit the speech or the presentation in 10 minutes. Go ahead, Doctor.
Yes, sir. Thank you very much. Can you hear me?
Yes.
The presentation was supposed to be made by Dr. P.C. Sharma, the director of the CSI Kannada, but because of some unavoidable circumstances, he is moved out from the institute. And on behalf of Dr. Sharma, I, Dr. H.S. Jat, Principal Scientist Agronomy, is going to present the presentation of Dr. Sharma. So excuse me for that. And the title of this today's presentation is Harnessing the Productivity from the Salt-Affected Soils and Indian Experience. As we are working on the salt-affected soils since last 50 years, as our institute is a nodal center for reclamation and the management of the salt-affected soils in the country, If you look at the global challenges of the salinity research, every minutes, every hours, we are losing almost 3 hectares of the lands because of the soil salinity and the solidity. And the soil salinity, it involves in all the agroecosystems, whether it is irrigated ecosystems, it is dryland ecosystems, coastal ecosystems, and the seawater ingresses and the other challenges issues. Since the nature and the properties of the problems, soils are diverse, specific approaches are needed to reclaim and manage the soils to maintain long-term productivity, because the saline soils needs different management, sodic soils need different managements, and when the soils are both saline and sodic, it needs different management practices and the approaches. If you look at the area under the salt affected soils in India, it is almost 2% of the total geographical area, and it is around 6.74 million hectare area. And by 2030, it will be around 11.25 million hectare area because of the expected climate change effects, because of the temperatures and the rainfall and the variability in the rainfall patterns. In India also, we are facing the 32 to 84% of the total groundwater use that is affected by the poor quality waters. So please previous slide. Yes. So if we see that we are losing almost from these salt affected soils, we are losing almost 50 million tons of the food grains annually, and that worth rupees 23,000 crores rupees. If we under the two categories of the salt affected soils, salinity effects and alkalinity effects, in salinity effects we have almost 5.6 million ton food grain losses we are having, and with rupees 8,000 crore, while in case of the alkalinity effects, we are losing almost 12 million tons of the food grains with rupees 15,000 crores annually. Next. In India, there are almost more than around 15 states we are suffering with the problems of the salt affected areas, but the majority of the areas are located in two major states. One is Gujarat, and that is located on the boundaries of the Arabian Sea, and another is the Uttar Pradesh, and it is the landlocked states, and it is in the upper part of the India, and it is in the lower Himalayan region. So this is the total area that we have, 6.74 million hectare area. Next. So if we are using, till that we are using the data from the 1996 base data, and if you see that in 3-4 states, the area under the 1996 in the Haryana, it was around 2.3 lakh hectares, but by 2016 it goes up to the 3.1 lakh hectares. So if you see the different data, we are expecting 10 to 15% more area under the salt affected soils in the country. Next. There, for the reclamation of the sodic soils, where we have the carbonates and bicarbonates of the sodium, calcium, and magnesium, we are having almost around 3.5 million hectare area, and out of that we have reclaimed almost 2 million hectare area. And the most important and promising technology that we have used was the application of the gypsum for the reclamation of the sodic soils. In the first year, we are having almost the yield of 4 tons and the 2 tons for the rice and wheat, but after 3 years we can get the good yields, and that is according to the national average of 5 tons for rice and the 4 tons of wheat. So by reclaiming these 2 million hectare sodic soils, we are getting almost 17 million tons more food grain productions, and also we are giving the employment to the large number of the peoples, around 310 million mandates, and we are benefiting almost 11 million peoples. Next. These are some of the apps and some of the software that we are using for the sodic soil assessment tools, and for that we are using, and it is already in public domain. These are the gypsum calculator, GypCal, it's a mobile app. GypKit, it's a kit that tells how much gypsum you want to apply for a particular crop, and this is another software is SQASS. This is used again for the calculation of the gypsum requirement, and also to predict the crop yields under the particular set of climatic conditions. Next. Next, please. Now, instead of the gypsum amendments, we are also developing some elemental sulfur-based formulations with some of the promising industries like Reliance, and from where we have developed 3 products. One product is suitable for the soils that have calcium carbonate content is more than 2%. Another product is suitable for the calcium carbonate of 1 to 2%, and the third product is suitable for the where the calcium carbonate content is less than 1%. So this is the recently developed amendments for the reclamation of the sodic soils. And the other amendments are the marine gypsum. We are working on the marine gypsums at the experimental levels. We are also working with fly ash, price mud, municipal solid waste compost, sewage sludge, and also the new area we are entering into the flue gas desulfurization, just to remove the sulfur dioxide from the flue gas that is generated from the fossil fuel based power plants. So we are working on that with the National Thermal Power Corporation of the India. Next. Next, please. Yes. This is the technology that is mostly we are using for the reclamation of the saline soils or the waterlogged saline soils, and it is spread already. We have covered almost 71,000 hectare area. And by doing this technology, we are able to improve our cropping intensity by 25 to 100%. Earlier, there were no crops without this subsurface drainage. And there is a yield increments of almost 45% in rice, 100% in wheat, and almost 200% in cottons we are getting from this subsurface drainage technology. Next, please. And we are working in a very close collaborations with the HOPP, Haryana Operation Pilot Projects, and its government-based projects. This is the new ventures. We are working with, in a very close collaborations with the Japan government under the GCAS project. Here we are testing these cut soilers just to manage the salinity, waterlogging, and the subsurface sodicity by the cut soiler. And our aim is to replace the gypsum requirement, replace the some part of the gypsum through the crop residues, because in north part of the country we have plenty of residues, more than 30 million tons of the residues we have from the rice and the wheat crops. So through cut soiler we can reduce the gypsum requirement by 50%. Not only this, we can reduce the subsurface sodicity by almost 20% with this technology. So this technology in the at the plot scale levels we are testing at the CSSRF farm. Next, please. This is the revision of the national groundwater quality map. As I already mentioned that the groundwater quality of our country is very poor, and almost we are having a poor quality water. Some of our saline nature, some of our sodic in nature, some of our containing the very heavy metals, and it is around almost 32 to 84% in the country. So not only this, that we have only subsoil soil surface salinity, but also we have the groundwater salinity in the country. So these are therefore we have a lot of challenges in the years to come. Next, please. Next, yes. For management of the poor quality waters, there are the number of methods we are using for management of the poor quality waters. One, we are using the gypsum bed technology. Through gypsum bed technology, just to neutralize the RSC water, residual sodium carbonate water, for neutralization of the gypsum, and it can be improved by mixing the gypsums and the placement in 4:1 volume by volume ratio, and in fact neutralize the RSC to the 6 milligrammes per liters. And beyond that, we are also using some of the conservation agriculture and the climate smart agriculture best techniques to manage the soil salinity. Next, please. Here in our institute, we are also developing the varieties for the cereal crops, for the cereals and the pulses crops. For the cereals, we have developed almost 12 varieties for the rice, and out of these 12 varieties, one is basmati rice, that we call it CSR 30. In wheat, we have developed 5 varieties, and in mustard, we have developed 5 varieties. For coastal salinity, we have 3 varieties, that is Sumati, Bhutanath, and Amalmanna. And for the chickpea, we have 1 variety, chickpea 1, Karnal Chana 1, and for the lentils, we have 2 newly released varieties, that is PDL 1 and PSL 9. And also, we are supplying the breeder seed to our stakeholders of all the crop varieties. Next, please. This is the field of the NAM farm Panipat. It is very near to our main stations, and this is our sub-stations where we have a salinity base. Next, please. And here we are working on the identification of the salt-tolerant lines for the different crops, like rice, wheat, mustard, quinoa, lentil, and chickpea. So this is the conditions where we have a salinity of almost more than 20 EC salinity we have. We are also working on the Salt-Tolerant QTL just to integrate into the mega varieties for developing the salt tolerance mechanism. For that, we have selected the 2 varieties, that is Pusa 44 and the Sarju 52, and in which we have already added the salt tops for the salinity tolerance. Next, please. Next. Yes. Also, beyond that integration of the salt genes, we are also working on elucidating the role of the osmotic, ionic, and the major salt responsive transcript components toward the saline tolerance in chickpea, and also on the genetic dissection and identification of the candidate genes for the salinity tolerance in case of the mustards. So, and these are, I think, they have published very good papers by the Singh et al. In Physiology and Molecular Biology, and also in the International Journal of Molecular Sciences. Next, please. 2 years back, and this is the genetic and molecular mapping of the salinity state tolerance at seedling stage in lentil. So this is the new area where we are working. Next, please. Some of the grasses we have also identified for the salt tolerant grasses for improvement of the salt tolerance in crops.
Eugene, please, because the time is finished for 10 minutes.
Grasses we have identified for isolation of the salt tolerant genes. Next, please. These are some of the products that we have developed for creating for avoiding the salt effect into the soils. And there are the number of the products we have developed: the Grosure, ICR Fugigant, Hello CRD, and then Hello Mix. These are some of the products, and all the products are the microbial consortia-based projects in which we have bacteria and fungi and their consortia that can help to mitigate the salinity effect on the crops and cropping systems. Next, please. This is the waterlogged sodic soils. Next, please. Waterlogged sodic soils are mostly in the central part of the country where we have different agronomic methods. for the land modification models for the waterlogged sodic soils of the southern semi canals, in which we have modified the lands as per our requirements to grow the crops in the dikes and to put the feces into the ponds. So this is the method we are adopting in the southern side canal area in the Uttar Pradesh. Next, please. This is again the sustainable management of coastal land through land shaping technology. In this technology, this is for the saline soils, and in which we are also shaping the lands as per our requirements to go for the paddy campus culture or the deep furrowed high ridge for cultivation of the crops on the ridges and for cultivation of the feces into the furrows. Next, please. Next. So this is the future perspectives that updation of the national database of the salt affected soils for 3 states, UP, Gujarat and West Bengal we have already covered. And tackling the subsoil sodicity and developing alternatives to the gypsum for reclamation of the alkali soils. Control drainage to reduce drainage effluent volume and conserve irrigation water and nutrients. Dealing with salinity, climate resilient crops and varieties, and biosaline agriculture, we have major focus on this. Then climate change impacts on the vulnerable coastal saline ecosystems, and I think there is a need to go for the human resource development and the ICTs for the salinity management. So I think this is thank you very much. Thank you very much to the organizers for giving us an opportunity to present our Indian experience in this conference. So thank you so much.
So, okay, thank you very much for your presentation and give us this opportunity to look in the Indian experience in salt management farming. I think this is a good opportunity to have some idea and technology that solve problem related to sodic soil and to high level of salinity and the management of that issue. Now we will go to our last speaker from California, Mr. Uli Sefertsen. He is the Chief Executive Officer of Desert Control. Mr. Uli in 2019 took this opportunity of climate and agri-tech startup Desert Control, followed by a passion for creating hope for a better future for people and planet. Mr. Ali advocates solutions to turn desert into fertile land, enabling climate-smart agriculture, forest and green landscapes. I welcome Mr. Ali for the next 10 minutes to speak about turning desert into urban land and reducing water consumption for agriculture in desert conditions with liquid natural clay. So the floor is yours, Mr. Oli, for 10 minutes, and the mic is yours now.
Thank you very much. So I'll start my presentation and let's see if everyone can hear me now. Right, and here we go. So our vision is really to make Earth green again, to foster the prosperity of basically all life on Earth. We have a vision to cultivate and green and recapture really 100 million hectares of degraded land in this current decade and contribute to sustainable social impact with significant water savings that will also help to balance our climate and the biodiversity of our planet. Desert control, we are doing that by focusing on areas of climate smart agriculture and technology development to combat desertification, soil degradation, and water scarcity. Our solution, which I will come back to in a few slides, is liquid natural clay, also referred to as LNC and liquid nanoclay, is a solution that can be used to restore and protect soils, reduce water usage, and increase yields for the areas that we focus on, which include agriculture, forests, tree planting, and also other green landscapes. So the drivers that we are focused on for doing what we do is really what other speakers have talked about here today. The increasing global population that we have that will drive a need for more food and water. And what we see is that water and water shortage will be one of the biggest challenges to meet in order to feed a growing population as we move forward. When it comes to desertification, which is one of the areas that is driving this increasing water scarcity as well, there are 110 countries in the world that are exposed to desertification, to land degradation, loss of fertile topsoil, and we see, according to the United Nations, that 12 million hectares of fertile land becomes barren and perish to desertification every year. Already today, more than 20% of the fertile drylands on planet Earth has been degraded. And if the current pace of degradation continues, there will maybe be less than 60 years left of farming for us. And the annual cost to the global economy is a staggering $490 billion US, according to reports from the UN. When we think about desertification, it's not just sort of the typical desert regions that are experiencing this. This problem is reaching way beyond these areas, and we see even areas such as in California, where I am right now, and the Midwest of the US, central parts and southern parts of Europe, countries such as Spain being at 74% of all the land territories at risk of desertification. So this is really a global issue, and it's also happening very much out of sight, out of mind, by our topsoils getting thinner and thinner from underneath. So it's something that will need to be addressed on a global level, where I think that work on sort of desert agriculture research, also very closely linked to managing saline soil environments that we're doing in desert regions, will have significant impact for other areas in the world as we go forward. When it comes to water as the biggest limitation for increasing food security and food production, the situation is that we're already today consuming more than 70% of all freshwater resources on Earth to support agriculture and food production. And as we lose more and more soil to desertification and losing the abilities for these soils to retain water and support growth, we will need even more water just to support current production, while we all know that we need to produce more food in the next 40 years than this planet has produced over the last 500 to support a growing population in a sustainable way. So this is why Desert Control invented liquid natural clay, liquid nano clay, or LNC in short. So what we've invented is a unique formulation process for turning natural minerals and clays into a liquid nearly as thin as water. We do this through a unique formulation process to create a liquid that can be sprayed directly onto the surface of the land areas. It can be applied through irrigation systems, through drip lines, through sprayers, etc. And when it's applied on the surface of the soil, it will percolate into the soil by the force of gravity, and nanostructure clay platelets will coat every grain of sand throughout this sandy soil structure, which in effect will give your sand structures throughout the soil a charge that is opposing the water molecules and also certain ions and cations, so that you retain water and nutrients in your soil and can cultivate sandy soils like agricultural soils, with the result of reducing water consumption by 20 to 50%, and also the fertilizer reductions, increasing the crop yields, and also boosting carbon uptake for these type of soils. When it comes to reducing the irrigation requirements for sandy soil environments, that's also a very important element when it comes to tackling salinity, especially because we are experiencing groundwater resources and other water resources and usage of saline water to cultivate our lands. And then to be able to retain that water in the soil and increasing the conductivity of those soils, so that you continuously also drive the salinity out of the topsoil layers, is very important. So the focus that we have had on developing this solution has been to have a non-intrusive way of treating our soils. That's why we focused on a liquid approach that can percolate into the soil by the force of gravity, without any intervention to the soil, without having to till or dig or turn or put physical substances in by mechanical force into the soil. And this also allows us to retrofit existing areas, existing planted fields, even green landscapes with this liquid. We've been applying it also to grassland areas through the surface without leaving any crust of the clay structures on the surface, which is a huge advantage when it comes to the approach of dealing with soil amendments. Our technology has been developed through 12 years of R&D up until 2017, when we established the Desert Control Company and also entered into the United Arab Emirates in 2018 to start external validation by independent research of our solution. From late 2018 through 2019 and 2020, we've run validation initiatives with International Center for Biosaline Agriculture. The first round of validations for grasses that documented 47% water savings for cultivating the LNC treated plots versus the controls. Also a notable reduction of the salinity in the topsoil, improved soil health, and better biomass production for this. Then we moved on to other agricultural crops. So through 2020, we did crops such as zucchini, pearl millet, and watermelon. Also here, significant reduction of water for cultivating these crops, and crop yield increases as well in the range from 17 to 62% as the result from this initiative. The LNC itself is produced in the field, locally in country, close to the areas where we are applying it, to avoid having to ship huge amounts of liquid around. So we have developed these mobile processing units in the size of a 20-foot tall cube container that we produce and apply directly in the field with. Right now we are in a scale-up mode, so we have all of these 4 units that we see here active in Abu Dhabi in the United Arab Emirates, and we're currently producing another 8 units like this to be able to continue our scale-up and also enter into the Kingdom of Saudi Arabia with our technology in the near future. Currently, we're also doing a larger initiative focused on improving food security in the Middle East in partnership with Mawarid and Barari. Here we are doing a variety of vegetable and food production in desert sand and desert soil, also looking at the reduction of water requirements and improvement of soil health for areas such as the date palm production, also for animal food with highly water-intensive crops such as alfalfa and panicum. Further, we are working on the green belts and the managed forests and looking at initiatives to reduce the water consumption and reduce the usage of saline waters as well for the salinity impact in these areas, looking at tree planting, looking at other permanent crops and fruit trees, and enabling food security with lower water requirements in desert conditions. Here we see some examples of applications that we've had in Al Ain in Abu Dhabi, where we're currently growing alfalfa and panicum. Here the liquid clay was applied through the drip lines that we see without causing any clogging or issues to emitters and filters and membranes, etc. Here we can see also the field growing in this current project that we're working on here. We can see some of the other crop varieties as well that we are working with. Here alfalfa as well as treatment of fruit trees, and I also want to touch on an initiative we worked on with ICPA in 2020 here, where we did the watermelon, zucchinis, and pearl millets. We called the initiative From Sand to Hope, and it was very inspiring to see the transformation of growing things in the desert sand environments here, sandy soil environments. In 38 days, we had a transformation from the left side to the right side here of this area of panicum, and we see the watermelon growth here, and finally the panicum. No, this was the pearl millet area that we in 5 months produced with very good water efficiency in the desert environment. And want to give a huge thanks to the International Center for Biosaline Agriculture team as well, who also, together with Red Crescent, we were able to make sure that as the pandemic hit, that gave us a strong reminder of the importance of local producers and food security. We were able to make sure that the fruits of hope from the desert reached people in need who didn't have seen any fresh fruits and vegetables for a while after the pandemic hit us. So if we look at the potential when it comes to restoring the degraded soil ecosystems that we have on our planet, it also has a major role to play in sustainability and balancing our climate. So analysis are estimating a potential of capturing and storing and basically offsetting as much as 6 gigatons of CO2 per year just by the restoration and rehabilitation of degraded soil ecosystems on our planet. If we in addition focus on enabling sustainable reforestation and stopping the deforestation on Earth, we can gain another 8 gigatons of CO2 offsetting with these nature-based solutions, which in total actually accounts for 57% of the reductions that we would need here for the 2DS target of the Paris Agreement that recently also was discussed here at COP26 in Glasgow. So big potentials for the future of soil and soil health management in these areas. I also think that we should look at agricultural opportunities in combination with other things such as the transition to green energy. I think plants like this can have a good opportunity of harvesting water as well as the sun in the fluctuations between daytime and nighttime and temperature changes, etc. And by using technologies to improve the water retention of the soils, the sandy soils in areas like this, we could basically also cultivate them to green these areas.
Don't close.
Lower the temperatures of these areas to increase the efficiencies of the panels and reduce the dusting.
Excuse me, can you go to the conclusion, please?
Is here, so maybe in the future we will have natural food forests combined with this in our ecosystems going forward. And that was my presentation. Thank you very much.
Thank you, Ole, for this presentation and providing these products for desert and for the arid regions and other regions needed to farm production and increase data productivity and saving water. Thank you very much. And now I will open the discussion for maybe 10 minutes because still we are ahead of our time. So I think Dr. Abid have a question. Please, Dr. Abid, if
Thank you, Dr. I highly appreciate. I think Minister already nicely and did a presentation. I think I really enjoyed. So I have a number of some questions. Like I think he has mentioned the technology LNC, which is I think very much relevant to our Saudi Arabia conditions, and also from the Green Initiative Saudi, and also from the Middle East. So I'm wondering about. He has mentioned that they're using the water for this technology LNC. So I would like Mr. Oli to explain what is the status of using the seawater as saline water with this technology. This is one thing, and the second, I think, what is the shelf life of such kind of from sustainability point of view? What will be the sustainability after using such kind of formula? I think that's very wonderful. That would be helpful for us. And third, lastly, what is the engagement? Such kind of for the farmers or for the state level. So I appreciate if you will accept some of these things. Thank you.
Sort of saline water and seawater. So in terms of what we have seen in our work so far, we see that we are able to increase the salinity tolerance of a number of crops with having an LNC treated soil. We are not completely at a sea level yet, but we've been able to increase it several thousand ppms in steps in terms of the salinity tolerance after the application of LNC. Also, we see that we have been able to take different grasses and the landscaping segment in addition to agriculture and enable the transitioning to treated water as well for these kind of areas without having any negative impact on the grasses there. But we're not completely at the sea level state yet, but we are very focused on seeing how far we can push this. When it comes to sort of the impact and duration and the sustainability of this, what we have seen in projects we followed so far is that we have a single application of the LNC to an area, giving a duration and a sustainable impact of this in a 3 to 5 year period, depending on a little bit how the land is managed, of course. So if you do heavy tilling and disking of the soil and mixing soil that is untreated from deeper layers into the topsoil, you may have to do a reapplication of this more often, but we see a good long-term impact of this solution. And as we're producing it locally in country as well, that's a strategy we've deliberately chosen to have a high sustainability of our approach.
Mr. Ole for the answer. I will go to Dr. Mark Tester regarding you talked about the proteins needed, and there are an increase in the protein needed. I think, can we consider quinoa salicornia as alternative plant-based proteins for the red meat proteins? This is the first question, and the second question I received from Dr. Ahmed Al-Jaber. How far, from your point of view, we can see crop grown in the field in upscaling farming with seawater, like the quinoa, salicornia, maybe rice? What's the time limited for growing these crops? Yes, Dr. Mark.
I'm not sure we'll be growing quinoa or even the fantastic rice that Rob Wing has been leading work on. I don't think we'll see that in seawater, really, not producing economically viable yields. They can survive, well, quinoa can't survive even in seawater. I think Salicornia, though, is fabulous, and I mean, it's already been grown, you know. For example, there's Alejandro Rios Galvan in the Mazda Institute who's been growing it, and growing this for seeds. The ICBA seems to be focusing more on the vegetative production, which is fine, of course, but I think the seeds are where big impacts can be made in the future. And he's having a go at doing this. For me, though, to really get an economically viable system in place using seawater, we really have to genetically improve these plants. I mean, all the agronomic work's essential, but my analogy is like going down to the edge of the highway and collecting a bunch of grass at the end of the year, at the end of the season, getting the seed out, grinding it up, making a loaf of bread, and expecting to make a living out of that. And I think this is really a push too far. I do think we need to genetically improve the Salicornia if it's going to get traction. That's a big task. This is a Neo-Domestication project. It's incremental, by the way. It's not just a switch. You know, one day it doesn't work, one day it does. It already sort of just works, maybe. But I think we will incrementally improve the Salicornia system as an economically viable system. I think incrementally, sort of in 3-5 years from now, I would hope we would be seeing some crops, and 10 years from now, I would hope it would be going widespread. I mean, the rice, I'd love it to work. I think that's a very, very exciting project that could be massively impactful.
Okay, I hope that I like this optimistic thought and this aspiration, Dr. Mark, and 10 years is not far away, by the way. If we'll succeed to see these crops grown in like seawater or brackish water with high level of salinity, this is a good achievement for globally, I think. And thank you very much. I will go just to our colleagues from India and regarding what is the solution you are proposing to manage the salinity with continuous irrigation, with saline water in the open fields? So can you just put some thought about it? And
where we have high EC, and for that we have almost covered almost 70,000 hectare area in the country, and we are also working in a very collaborations with some of the state governments to promote this subsurface drainage technology. These are the simple drainage pipelines that we install below around 1 to 1.5 meters below the soil surface, and through which we installed these subsurface drainage lines in the areas where we have a very high water table with saline nature. It is around 2 meters from the soil surface. So when we go to heavy rainfalls, then the water table comes up toward the soil surface, and that water moves out of the drains. This practice we are following in our country.
to ask a question. Yes, ask Fahad.
Please unmute yourself, not audible. Please unmute.
Unmute yourself, Fahad. I will ask the question. I think he will ask about Mr. Neil about.
Mr. Neil asking the question to audience.
No, you can hear me now?
Yes, go ahead.
Okay, thank you. I'd like to thank the Ministry to organize this valuable conference, and many thanks also for the speakers for their valuable presentation. My question to Ali: what's the percentage of your mix? There's fertilizer, water, and the clay, and what kind of clay you're using, and how to inject this mix to the in the soil?
Okay, so in terms of our liquid natural clay combination, we basically start with an approach where we do soil samples of the target area before we decide on the formulation. So basically, there is no fertilizer in the mineral structures of the liquid clay itself. It's purely natural minerals, and we compose these minerals to match the target soil in terms of understanding the mineral composition of the target soil, the pH level, the salinity of that soil, and the combination with also maybe what you're going to cultivate there, because different clay structures and different mineral structures have different surface charges that are very relevant to how we shape the formulation of this. And then when we formulate it based on the target soil, we will also formulate it based on how we are going to apply it. So we ensure particle sizes to be compliant with, for example, irrigation systems, drippers, emitters, etc. if we are applying through there. But we can apply it through manual spraying. We can also do for tree planting or treatment of trees after they have been growing for a while, or growing forests by a combination of surface application that will, by the force of gravity, this liquid will percolate into the soil structure. It will coat every grain of sand throughout the soil structure, and also we put in larger particles that will form the phenomenon called clay bridge bindings that give you a very high level of porosity in the soil. So you're not getting a clay soil at all. It's a very light enrichment of clay that we apply to the soil. Maybe a square meter or cubic of soil is less than 1 kilogram of raw material clay that we actually apply on a nano format, because we we extract the clay platelets to its smallest denominator, a platelet thickness of 1.4 nanometer. So we get an enormous surface area out of these particles, which makes it extremely effective to apply to the soil. And we can apply to any kind of surface-based application, slurry wagons, water wagons, sprayers, etc., and using also implemented irrigation systems that are already in place.
The last question by Mr. Nell, please. Mr. Nell.
Hi, I don't have my video on yet. Mr. Sigurdsson, can you tell us what it costs to apply LNC on 1 hectare versus the value of the increase in watermelon that you would see from that application?
Yeah, I mean, in terms of the economic calculations, we've run several business models on both the saving of water and the increasing of crop yields, and the average sort of return of investment that we have seen on this in the environments where we've been working has been a payback time of on average 1.7 years of payback time. And then we've had a basic cost structure in the range of, well, we're getting the cost structures sort of as we reach higher scales to different levels, but that's been on a cost structure of $8,000 per acre or $20,000 per hectare in sort of a guiding cost line for that, which is quite much cheaper than, for example, biochar and these kind of amendments, and also much easier to apply since you just have surface application and self-percolation.
Thank you.
Thank you for all of you, and I will now go to the heading towards our third session, case studies disclosing best practices to unlock the potential of seawater farming and saline agriculture. In this session, we have 5 keynote speakers. Our first speaker is from the United States of America, Mr. Bill Speckman, founder and CEO of Regenerative Resources. Prior to starting Regenerative Resources, Bill was co-founder and director of the Al-Badia project in Mecca, where he worked in prototyping, Hima restoration and forest establishment in the mountain of Hijaz. And Mr. Nell has won multiple awards for his work internationally. Now I am pleased to welcome Mr. Nell to present regenerative seawater agroforestries. Please, the mic is you for 10 minutes, Mr. Nell. Go ahead.
شكرا جزيلا والسلام عليكم للجميع. أبغى أستاذن منكم صوتي. أنا تعبت شوية من دوبي رجعت من كوب 26 وتعبت شوية من السفر بس أستمر بالإنجليزي من هنا. Co-founder of Regenerative Resources. We're a company that transforms degraded landscapes into productive agroecologies. I do have a couple comments I want to start with, given the content of the of the conference to this point. The most important being that any kind of monocropping system, whether it's grown with fresh water or seawater, will be subject to the same problems and foibles and measures of unsustainability. And I assert that agroecologies, particularly seawater ones, have significant potential both in the Arabian Peninsula and in many other areas as well. And I will talk you through what we call our regenerative seawater agroforestry. This is an 8,000 hectare site that we are purchasing in the next 4 months on the Pacific coast of Mexico. You can see it is completely degraded. There is no photosynthesis on the site. You can see the salt pans. You can also see a degraded shrimp farm there. And we are transforming it into this, which are a series of mangrove-based and halophytic agroforestries. We start this system with aquacultures. Aquacultures have two fundamental problems the way they're currently practiced, which is that the effluent from aquacultures create more hypoxic zones in the ocean per kilogram of production than any other agriculture on the planet. They are extremely polluting and cause massive dead zones wherever they are established, including the farms down in El Leith that I visited back in 2019. The second fundamental problem with aquacultures is the feed. Typically, an aquaculture feed is 1/3 wheat, 1/3 soya, and 1/3 bycatch. Not a single one of those components tend to be produced in a sustainable way. This is a system that solves both of those. What we do with our aquaculture effluent is we pump it through this system, and that is the source of nutrient. Okay, the nitrogen, the potassium, the phosphorus, and the trace minerals that we get out of the ocean provide the fertilizer for growth, which means that we can eliminate the need for purchased fertilizers. That is provided by the aquacultures that we do. And then we have a series of, what we're doing is we're taking very traditional agroforestry techniques, such as alley cropping, integrated pest management, coppicing, and constructed wetland systems in order to absorb that effluent, and in turn we can produce the feed for the aquacultures. We have 3 different aquaculture feeds in development. We're about 85% of the way there to being able to provide 100% of the aquaculture feed off of what we're growing off of this system, in addition to a whole lot of other products, such as mushrooms, spirulina, biofuels, animal fodder, algae, both micro and macro algae, artemia, salt, bivalves, oysters, etc., etc., etc. This is an extremely productive system that we install on landscapes that are currently wastelands. I'll skip the impact because I want to get to the applications. One of the most important for the Middle East is fodder and feed. We can produce fodder and feed with no fresh water at all. We are involved in talks to go into the Horn of Africa and into Madagascar, which are very famine-prone areas specifically for this purpose. Food security should be obvious here. We're not using any fresh water at all. We're not desalinating. We're not diluting. This is 100% seawater to produce a whole lot of food in an agroecological system. The ecosystem services provided by this are significant. In the first project we did in Eritrea, we saw a 1,000% increase in biodiversity. We know that this system, when built right, will be carbon negative, and we are actually selling carbon credits as part of the way to fund these developments. But beyond that, protection from hurricanes, storm surges, and potentially even sea level rise are all significant environmental benefits. For the Hejaz in particular, this increases freshwater resources by intercepting flash floods. In Eritrea, we began to fill up the shallow aquifers instead of those floods running into the Red Sea. That has huge potential for the Hejaz. We can do both micro and macro algae within these systems, which have a lot of promise in the use of biotech, bioplastics, biopolymers, and other industries. And then we actually cooled the local climate by 2 degrees Celsius when we did this in Eritrea. That's a picture of the Eritrea project right there. So cooling, jump-starting a small water cycle, in addition to the other environmental benefits, in addition to food production and job creation on otherwise very desolate landscapes, is what we're all about and what we're trying to do. This is a site we're working on in Spain. It used to be a marsh. They built levees along the river, and the river is very salty. We're doing multi-trophic aquacultures with halophytic systems and seagrasses. In northern and more southern latitudes, these are seagrass rather than mangrove-based systems. But in places like the Hejaz, the Red Sea, Ghana, Mexico, northern India, and Australia, these are mangrove-based systems. On this particular project, we will grow 45 million mangroves, and our estimated IRR without the carbon, but with the real estate, is 19%. So these are profitable systems when sited correctly. We design them according to local ecologies and to local markets, and that's what we're doing at Regenerative Resources. Thanks, folks.
Back to you. Back to you. In the discussion. So we will now, I am glad to invite our second speaker from Pakistan, Dr. Balqis Gal. She is the director at the Institute of Sustainable Halifax Utilization, University of Karachi. Dr. Gal is mainly focusing on developing non-conventional crop for saline land and saline water. Now she is with us virtually for 10 minutes talk. I welcome her to present food security in arid region of Pakistan, a new paradigm. So the mic is yours, Dr. Balqis. Please limit your speech in 10 minutes. Thank you.
Thank you, Dr. Salman, and honorable speaker and guest. Assalamu alaikum and good afternoon. First of all, I would like to thank Dr. Salman Ali Al-Khatib, Director General, for inviting me and giving me an opportunity to discuss about some very important environmental problems and their solution on this forum. So today, the topic of my presentation is food security in arid region of Pakistan, a new paradigm. Okay. So, as you all know, that the arid regions where the rainfall is below the 100 millimeter extend from Rajasthan to all the way up to Morocco. In that region, the primary thing is the water is in very short supply. In addition, the salinity is also increasing there. About 1 billion hectare of the world land has become saline due to several factors. Some factors are, one is the primary salinity and other is the secondary salinity. Primary salinity because of the natural causes, and the secondary salinity is due to man-made causes. So there's a lot of people says that the freshwater supplies decline. Supplies not decline, the consumption is increasing. So Pakistan has 500,000 cubic feet per person per annum. In 1947, it has gone down 118,000. If the population increases continuously, its utilization in agriculture and in the industry will be continue, and we will become a water deficient country very soon. Next slide. So there are two major problems: soil salinization and viscosity of the water. We have a lot of resources of subsaline or subsurface water available in Pakistan, but almost 85% of them are saline. overall poor quality and that cannot be used for conventional agriculture. What are they called? Overall, what we gone now, it's about 15% of the world area, which is abundantly agricultural land is saline, and it's increasingly becoming saline. So if you want to maintain at the same level as they now, about productivity has to be increased at one time. We have rapidly growing population, specifically in the area where this problem is the major problem. At the same time, the land becoming saline due to several reasons. So this means a big disaster. So we need to do something to overcome that. Excuse me, I'm sorry, there's something. Next slide. So desertification, salinity has become continuously increasing as the progress. 1 billion hectare of the land is already become saline due to several factors. And available fresh water is very low, and according to US Census Bureau international data, this report, due to increase in population rate, all the resources are going down very fast. As you can see in this picture, the rate of population increasing rapidly, and it will become 9 billion at the end of 2050. Next. Okay. So food security is the major problem in our region. To overcome that problem, we can open new land for agriculture, but then opening new lands has a lot of consequence, ecological consequence, as well as we do not have enough fresh water available to those lands. So that's why new land is very, very difficult to open. In Pakistan, we are mismanaging in our agriculture irrigation through canal system at one side. They are increased productivity of the agriculture. On the other side, it has substantially increased salinization of the land. And about 400,000 hectare of land will becoming saline every year. And about total 60% of land is already saline in United States, as I'm right. I'm not saying that this cannot be done, because, but this may take another 10 or 20 years to really get some incredible results. We don't have that much time. So works are going on. So what should we do next? Oh, sorry. So what is the best available option? Best available option is that those plants which can grow in highly saline area and produce considerable biomass, which are called halophyte. We look the alternate solution here. We are not fighting with the nature. We are not trying to introduce salt-tolerant here. We are just using it of the nature for the benefit of humankind. And that exactly was the intent to do this. Next. So everyone knows that there are several potential uses of halophytes, and we can use halophyte as a food, forage, fuel, and biodiesel, and etc. There's several others. Next. So next. So if you want to do this, then it is necessary to create an institution that can primarily focus on this and lead to development of this kind of crop. And I'm really very grateful to Higher Education of Pakistan for providing us enough grant, not only to develop this institute, but equip with the most modern equipment available. And next slide. Next. Yeah. So, University of Karachi syndicate approved naming our institute Institute of Sustainable Halophyte after the late Professor Dr. Muhammad Ajmal Khan. The University of Karachi syndicate meeting unanimously approved the name of the institute after the name of the Dr. Ajmal Khan. So the new name of our institute is the Dr. Muhammad Ajmal Khan Institute of Sustainable Halophyte Utilization. Next. Next. So our vision is basically is that we want to use saline what we want can be productive. So our wasteland should become productive, and our wasteland should take care of poor farmers, especially I'm referring to the farmers very poor living in Balochistan and other part of the Pakistan. Next. In our institute, we were very ambitious, and we took a lot of different projects, like from plant halophyte distribution to ecophysiology, and then biochemistry and metabolomics. So we want to know how many halophytes we have in Pakistan, and then how we can use this all. This work is in progress. The only part, the later part, the biochemical and molecular argument, I will tell you brief. Next. We have already cataloged the number of halophytes in Pakistan, and we are very fortunate that we have about 410 halophyte species found in Pakistan, which is almost 15% of the total halophyte found in all over the world. Next. Next. Next slide, please. One of the major problems in Pakistan is fodder for cattle. And after screening, we select the best candidate for fodder. And next slide, we have already a feed crop growth system, develop a feed crop growth system that can be managed with brackish water. Panicum turgidum can grow in brackish water and salty soil, accumulating itself. Co-cultivation with grid of swida, a salt accumulating halophyte, kept the soil salinity stable. Next slide.
Dr. Gul, please just go to conclusion. We are,
Okay, next. So, we have already patented this agriculture, this growth system. And right now, I am working with the Sindh Anglo Coal Mining Company, and we are working on a biosaline fodder plantation project at Third Desert, Pakistan. So I think I will skip if I don't have much time. So we can achieve the Sustainable Development Goal for water and recognize how important water is a value driven for agriculture and for energy for all other goals. Thank you very much. Due to the shortage of time, I can't continue my whole presentation. So thank you very much again for your attention.
Okay, thank you, Dr. Balgis Gaul, for this presentation and this thoughts in Pakistan. I think this experience is full of information, and I think I referred in my publication to Dr. Ajmal Khan in many of his papers presented or published in the Halifax, and I think he is a great man dealing with such difficult subject. Thank you, Balkis, and I will go to our third speaker in the from France, Dr. Didier Basel. He is a senior scientist based on CIRAD biodiversity at FISO. Dr. Didier is an active researcher in agroecology with a focus in agrobiodiversity and plant genetics resources. He has wide international experience in Africa, Asia, and South America. I welcome Dr. Didier for the next 10 minutes to present Quinoa's experimentation and the production in the Mediterranean region. So the floor is yours, Didier, for 10 minutes, please.
Thank you, Chair, and good afternoon for everybody. It is my pleasure to be with you today. First of all, I want to thank the organization for giving me the opportunity to share experiences with you during this important international workshop. I spent 2 years at FAO headquarters and I developed experimentation of quinoa in more than 30 countries, and I want to present today some experimentation around the Mediterranean Sea with you. Next slide, please. So biodiversity conservation is today a key global concern of the international community with the light IP-based IPCC and FAO global assessments. In Latin America, the Andean Altiplano is one of the centers of origin or hotspot of the world's biodiversity. And during thousands of years, the population have interacted with the agro-ecosystem, and quinoa crop has evolved from a complex of biological, geographical, climatic, social, and cultural interaction that have determined its current high genetic diversity. Next slide, please. The declaration by the United States in 2013 as the International Year of Quinoa aimed to draw the global attention to the role of quinoa biodiversity and nutritional values in food security and poverty eradication in order to achieve the Millennium Global Development Goals. Next slide, please. Quinoa was domesticated near the Lake Titicaca between Peru and Bolivia. Quinoa diversity at continent scale has been associated with 5 main ecotypes: islands in Peru and Bolivia, intermediate valleys in Colombia, Ecuador, and Peru, salt flats in Bolivia, northern part of Chile and Argentina, tropical yungas in Bolivia, and the sea level ecotype, coastal of lowlands in Chile. Among these 5 ecotypes, 2 ecotypes are very tolerant to salinity, the salt flat and the coastal ecotype. Next slide, please. Thanks to its extraordinary genetic diversity, the crop is highly adaptable to different agroecological conditions, and the crop is tolerant to frost, drought, and salinity. And the differences are very pronounced between all these 5 ecotypes. Each of these ecotypes is associated to specific conditions of altitude, latitude, and is adapted to specific soils and climatic conditions. Considering its origin in central and southern Chile, the sea level ecotype appears as the most adapted to temperate and Mediterranean environments. And with high attention to the Chilean germplasm, the number of quinoa producing countries has risen rapidly from 8 during the 80s, 40 during the second thousand to 75 in 2014 until 121 today. Next slide, please. So from at least 5,000 years ago until the beginning of the 80s, Chenopodium quinoa grain has been specific to the Andean countries of South America. Next slide, please. But since the other countries understood the potential and benefits of quinoa, the amount of experimentation conducted did not stop growing, and the spread of worldwide quinoa is made from strong relationship between institutions that share their genetic materials. Next slide, please. During the past 30 years, quinoa was tested in all the continents, and nowadays quinoa is cultivated in more than 125 countries. Quinoa globalization entails challenges to the countries of origin, and these are important to consider for future development. Understanding this reality is fundamental to face the challenges of conserving local biodiversity, developing and promoting new varieties, and cooperating on plant genetic resources exchanges with inclusive processes toward fair benefits with Andean countries. Next slide, please. Now, I will present the different steps of quinoa development in the Mediterranean. Next slide, please. Quinoa arrived first in the southern part of Europe during the 90s. Next, please. The project American and European test of quinoa was the first wide diffusion of quinoa worldwide and underlies the current global expansion of the crop. Field trials were established in several countries such as Spain, Italy, Greece, through the first network of international cooperation for promotion of quinoa. Quinoa crop was tested as an alternative to cotton and tobacco cultivation. The increase of salinity and degraded land were also a factor of adoption of quinoa crops. It also appeared in Morocco at the end of the 19th as a restrict crop to fight against abiotic stresses for local crops. Next, please. The second wave was observed before the International Year of Quinoa by some countries who wanted to benefit of the high nutrition value of the crop, recognized by consumers of healthy organic products. It offered new incomes to small-scale farmers through diversification of their cropping system. Next, please. But since 2014, all the countries all the Mediterranean Sea are testing or producing quinoa. And the key factors for its development were the quinoa high tolerance to salinity and resistance to drought. Next, please. The strong interest of quinoa in the Mediterranean has two objectives: to help fight malnutrition and to help reduce poverty, because quinoa grains have high nutrition value with all essential amino acids, mineral, vitamin, etc. It is a restricted crop that can grow from sea level to over 4,000 meters of altitude. Next, please. But today, first, new country producers have difficulty for entering quinoa grain into national markets. Next. And second, seed legislation at global level limits the access to quinoa genetic resources for testing the crops under new environments. Next, please. And third, the main objective of the trials are not so clear for some countries today. Next, please. An objective of adaptation from existing consequential variety differs very and completely from a strategy of clone breeding for developing new cultivar. Germplasm and experimental design for the trial may be adapted to the objectives. Next, please. And fourth, training both farmers and agricultural advisors is essential for developing a complete quinoa value chains. Next, please. Existence of commercial varieties facilitated access to seeds for quinoa testing, but not to high genetic diversity for quinoa adaptation. Despite of the immense quinoa genetic diversity, it is not currently used to the food due to this lack of access. So a new strong relationship between institutions that can share that plan that genetic material could be supported through research network, respecting legal regulation on seed. It is one of the coverage seed of the global collaborative network on quinoa, Quinoa.org. Next, please. So in conclusion, drought resistance, salinity tolerance, and exceptional nutrient value are some of the advantages of quinoa to face the effects of climate change in agriculture. But access to genetic resources is necessary to allow the adaptation of an exotic species. Research plays a central role in the development of quinoa through international collaboration, but it is necessary to be patient before expecting commercial production. Next, please see here some important documents for going forward. This paper relating to the experience of 9 countries testing quinoa under arid and saline conditions around the Mediterranean. Next, please. This document concentrates all the information in the state-of-the-art report on quinoa around the world, co-published by FAO and CERAL in 2015. In the next one, this book presents the challenges of the conquest of quinoa for the world. Next. Thank you for the listen.
So thank you very much, Dr. Basel, for this presentation and about quinoa, which is an important, I think, candidate crop species for saline agriculture and farming. I'm glad to invite our next speaker, Abdulaziz Haresh from Morocco. Dr. Abdulaziz is a horticulture scientist specialized in land and water resources management. He has worked as a consultant in EU funded and now affiliated with African Sustainable Agriculture Research Institute in Mohammed Sadis, 6 Mohammed Polytech University, Morocco. Dr. Abdulaziz, I welcome you for the next 10 minutes to talk about introduction and upscaling of alternative forage crops under saline condition, case study from the south of Morocco. So the floor is yours, Dr. Abdulaziz.
Thank you, Dr. Suleiman. Do you hear me, Dr. Suleiman?
We can hear you very well, and we can see you also.
Very good, thank you. So thanks again for the invitation. This is very interesting, actually, workshop tackling this very important project. So I will be fast. I will just give an overview about our research and development project that we are undertaking here in Morocco, especially regarding the introduction and upscaling of forage crops and other crops. So we are in the African Sustainable Agriculture Research Institute. It's a new institute created by UNCXP University. It's now the biggest university in Morocco with high standards. And now we are in Laayoune, working on Laayoune in the south of Morocco, so working on different thematic related to biosaline agriculture and other thematic. Next, please. So as you know, we have in the desert environment here in the south of Morocco, which is similar to the desert environment in other countries, Saudi Arabia or UAE or GCC country in general. So we have many challenges. We have an arid climate, which is characterized by a low rainfall, which doesn't exceed actually 40 millimeter a year. We have a relatively low level of production of a traditional forage crop like alfalfa corn, and also the most important, problem we have is related to groundwater salinity. The salinity in the region is over 4 grams per liter in most of the region. So do we have a great potential actually to valorize saline resources, and also we have a great potential to introduce biosaline agricultural system and also the alternative forage crop as a new solution, or as a solution to valorize the saline water. Next, please. So we started first, this is the approach that we did in our project. We started first by the first stage of the project in 2015 by introducing mostly 15 species of forage crop in a typical area where we have a forage production system based on traditional forage crop like alfalfa and forage corn. And you can see the salinity in the map. The salinity is getting higher in year after year due to over-exploration and also due to the seawater intrusion, because this area is near to the sea. So the idea was to test in the beginning, at small level, to test several, forage crop, and then to do also upscaling in the next stages. Next, please. So we tested several crops like Hispania, pear millet, sorghum, barley, quinoa, blue panicum, triticale, fodder beet, and other crops as well. Next, please. And I'm just here presenting an overview about the result that we have obtained. You can see from the comparison, we have the alternative crop for forage crop and the traditional forage crop, and you can see the differences actually of the both cropping system. You can see, for example, this Hispania is doing very well. We are exceeding 100 tons per hectare. So blue panicum also, so we are exceeding, especially even under low and high saline, because blue panicum is quite a bit halophite, forage species, and it's doing very well actually in the south. This is what we see in the next slide. Next, please. So what we did in the second stage of the project, we are actually undertaking the second stage. So we passed from the control condition, from the introduction trial to an upscaling trial. So we have established 7 demonstration platforms in the whole, in the south of Morocco. So in different agroclimatic zone to, have a clear, result, a clear idea about the crop performances in different locations. Next, please. Because there is actually a gap between when we conduct trials under experimental farm condition. It's not the same like you conduct trial under farmer's condition. Farm condition is quite a bit different from the controlled conditions. So we wanted to know exactly what is the performance of this crop, and this is just a preliminary result. But the most important here is that we tested these different crops and the different salinity level and the different platform, as you can see in the graph, like in the right side. And you can see that we have different salinity level, and we have in the other graphs we have the performances or the forage yield in terms of fresh biomass of different crops. So we are testing barley, oat, triticale, maize, pear millet, sorghum, quinoa, also fodder beet, panicum, Hispania, so several, almost 10 species that we are testing. And you can see that there is a huge or great performances actually for blue panicum, for fodder beet, for barley and other cereals as well, that they are doing very well in all the platform condition with different salinity level. Next, please. So it's good actually that my friend Didier passed before me, because he was introducing some information about Morocco and how quinoa was introduced in which year, etc. So the second part of my presentation will be dedicated to the quinoa value chain development in Hamna region. So first,
First, we did like a farmer survey to assess actually the adoption of quinoa, to know how many farmers that are cultivating quinoa, and how many farmers that have never heard about quinoa, but they are interested to grow quinoa. Actually, you can see the result in this graph. So we have almost in the region more now. Actually, we have more than 100 farmers practicing quinoa, and we have also, according to the survey, that more than 250 farmers are interested actually to grow quinoa. Please, next. So we did some introduction trial for some new varieties, because we had already introduced varieties like the common varieties, the Titicaca, Punu. So we had, but the productivity actually over the time is getting lower because, you know, the loss of the genetic performances. So what we did, we introduced new varieties from ICBA, and you can see the differences actually when we compare ICBA varieties with other, you know, varieties. We also, tested some practices like irrigation and also application of manure as organic amendment. And you can see the differences actually when we pass from rainfed to irrigation, we doubled or we tripled actually the production, and the more we improved actually the yield even under manure or under organic amendment. This is just to show the interest and the importance of, you know, irrigation and organic amendment in the case of quinoa. Next, please. So what we did in this project, that we did an analysis of the whole value chain of the quinoa in Morocco. It's a basic actually value chain. Of course, we have different components, we have different actors that they are involved in the quinoa value chain. From the production point of view to the post-harvest and transformation to the processing, distribution, etc. Next, please. What we did in this project also is that we have been working on quinoa valorization, especially with some actors, with stakeholders like the women cooperatives, that they are doing the processing, for example, making recipes like bread, like sweets, Moroccan sweet, Moroccan couscous, and other products. They are actually marketing them in the market, and the market of quinoa in Morocco is actually significantly increased, but still, as DD actually emphasis, that still we have a lot of effort to do in the market and to access to a large actually community of consumers. Next, please. Also, to make more, achievements in terms of the marketing, in terms of awareness, etc. We did, several, promotion activities. So we did some tasting, sessions. We have been, participating in a lot of several fairs, etc. So we are supporting the cooperative to showcase their product to larger community, and actually we are starting to see the result of the promotion activities that have been done. Next, please. Also the capacity building when it comes to introducing upscaling new crops. So farmers didn't know about them, so we need to make a lot of effort in the capacity building. So we have been conducting several sessions for women, for the extension, agents, for technician, engineer, etc. Next, please. So I will actually, take this opportunity, okay, to announce that we are organizing the second International La'youn Forum on Biosaline Agriculture in collaboration with NDPE. So we, if you excuse me, Dr. Suleiman, I will just announce this forum or international conference. This is the link. The deadline is 30 December. So if any one of you interested to submit an abstract and to participate with us in this conference, so please, you are welcome. So we have the link in the slide. Please, next. So we are also, organizing another special issues, and a special issue that will be with the conferences, but actually we are inviting any, scientists working in the biosaline agriculture to submit, papers to this special issue about advance in biosaline agriculture. It's with plants in DPI as well.
And by this slide, I would like to thank you for your attention, and also again, thanks for the organizing committee for inviting us to this interesting workshop. Thank you.
Okay, thank you, Dr. Abdulaziz, and I'm grateful for this presentation and experience regarding forages and quinoa in Morocco. I will go to our last speaker, he's from Netherlands, Dr. Arjen de Vos. I'm happy to share that he was also the part of our previous compact desertification workshop done here in person in Saudi Arabia 2 years ago. Dr. Arjen is the founder and director of the Salt Doctors. He is connected with us virtually to present challenges and opportunities for potato and vegetable production under saline field conditions. And the floor is yours for 10 minutes, Dr. Arjen. Yes, please.
Yes, thank you, and thank you for the kind introduction, and of course the invitation to be part of this workshop. It's a lot of interesting presentations, and I think it's an honor and also a challenge to be the last presenter of today. But I'll try to keep it nice and practical to keep everybody on point. And I would like to present some of our work that focuses more on potato cultivation and vegetables. And I also like to explain during the presentation why we are focusing on these conventional crops. Next slide, please. So I think the global salinity map has been mentioned before. And yeah, there is a lot of salt affected land, of course. The new publication already identified 833 million hectares of salt-affected land based on 70% of the area mapped. So as you can see in this image, not all the land has been mapped already, especially China, North Africa, Saudi Arabia. There's no data yet uploaded by the countries themselves. But in short, and that's also what you can see in the table, is that actually the majority of these salt-affected lands are only slightly to moderately saline. So that also raises the question, do you really need highly salt-tolerant plants to adapt to salinity, or can you also use slightly or moderate tolerant crops? So that was the question we asked ourselves already many years ago. Next slide, please. So we started doing large-scale screening and determining the salt tolerance levels of conventional crops in the Netherlands. So more or less 8 years of research under controlled field conditions. In that time, we screened up to 800 different varieties of 50 different crops. And our idea was, if you screen enough varieties of specific crops, then it's highly likely you will find some varieties that are more tolerant than the conventional varieties that a lot of farmers are using. For instance, potato, it originates from the same area as quinoa. Well, that crop has been mentioned, discussed a lot of times in the different presentations today, of course. So there are a lot of natural salt-affected areas in Latin America. And also potato originates from those areas. So if you can start screening potatoes, can you find varieties that are more salt tolerant? And the same, for instance, is true for the beets. All these beets have been domesticated from the sea beet and sugar beet, fodder beet, the leafy beet, which is used in many countries as a spinach, the red beet. They all remained very salt tolerant. So you don't even have to do a lot of screening, but those are examples of conventional crops that are very suitable for moderate saline conditions. And we also found from carrot, cauliflower and cabbage some very interesting varieties that you can cultivate under saline conditions. And yeah, the most interesting part, I think, is that farmers know these crops. They have a very good nutritional value. The whole value chain is in place already. So the potential impact is very large if you can use salt-tolerant varieties of conventional crops. Next slide, please. So understanding the problem is always our first part, what we are doing. So we always have a very practical approach. We want to understand the local conditions, look at the local salinity levels of the soil, the water, the current cultivation practices, the climate, of course, because that all determines the choice of your crop and the variety that you can use, including the different market opportunities. But yeah, in short, we do a lot of salinity assessments, but also practical trainings in the field to really understand the local conditions. Next slide, please. So, yeah, based on the knowledge that we gained with the 8 years of R&D in the Netherlands, and together with understanding the local conditions, well, then we of course want to see if these varieties that we identified in the Netherlands, which of course is a very different climate zone, if those varieties are also suitable for the local conditions, looking at soil type and the climate, day length, you name it. Well, here you see some images of our work in Egypt and Pakistan, where we start validating the potato varieties, first under controlled field conditions, also working together with commercial breeders. We also assist them with their selection trials and breeding programs. So then you really want to see, okay, which varieties are most suitable for the local conditions. And as said, that's not only salinity, but also climate, and the market should be taken into consideration. Next slide, please. So these are two examples of the implementation of the potato cultivation. So we worked in Pakistan, and only there the introduction of a more suitable potato variety for saline conditions already resulted in a 42% yield increase under moderate saline conditions. So the soil salinity levels there, we worked on more or less 10 hectares. Average soil salinities were 8 decisiemens, so that's moderate to high saline conditions, but we still managed to get a 40% yield increase, and these potato varieties are still being important at present day. And also in Egypt last year, well, also moderate saline conditions, we tested several varieties, and the best varieties under these saline conditions and also organic conditions yielded 32 tons per hectare, and the national average is 27 tons per hectare under non-saline conditions, conventional agriculture. So compared to the national average, we have a very interesting yield increase already, and these salinity levels are very common in Egypt and Pakistan. So there's a lot of potential for further upscaling of well, at least these potato varieties. Next slide, please. So we're of course working with other crops as well, not only in Egypt and in Pakistan. We do a lot of work on the halophytes in the Netherlands, but also working in Southeast Asia, we're in Bangladesh, Vietnam, working in Kenya and Jordan. So it's all about first piloting and validating the crop performance under the local conditions. So we usually do that maximum 1 to 2 hectares to really validate the growth performance and work on the tailor-made cultivation strategy, because as was indicated already, of course there's always a very complicated interaction between your crop and your soil and your water. So you really need to understand the local conditions, identify the weakest link, and if your soil and water is not in order, then also a salt-tolerant crop will perform very poorly. And again, we really focus on crops with good market potential for the farmers, so there's also the upscaling potential. Next slide, please. So this is an example of an integrated solution that we're also working on in Egypt, in the Fayoum. So there's a heavy clay soil, and the water infiltration and the drainage is a big issue, and the same with saline groundwater that's quite shallow, and through capillary rise, that's really the source of your salinity. So if you understand the source of the salinity, you can really work on focused solutions. And in this case, we wanted to plant Sesbania to improve water infiltration, to improve the drainage, and in time also lower the soil, the groundwater levels to minimize or stop the capillary rise of the saline groundwater. It's also a very good source of organic matter. Can you go back to the previous slide? Yeah, thanks. It's also a very good source of organic matter, So mulching, improving the organic matter content of the soil. Of course, it helps to improve soil conditions, improve soil fertility, but also by improving organic matter, where you can link that to a lot of different positive effects, including your water retention and carbon storage, for instance. And later on, we want to do intercropping to start introducing the more conventional commercial crops as well. So then you have this intercropping with agroforestry. Next slide, please. So another aspect we're working on, we developed this first in the Netherlands, and now we're piloting it as we speak in Tunisia, North Africa. Of course, that's the hydroponic system, and we really focus on the open field and a low-tech system, so it's also a low investment for small and medium farmers. And this system is very interesting from the point of view that you can also use saline water and you don't have the issues with infiltration, leaching, drainage, taking care of your water resources that you're not polluting. So it's a simple system, growing plants directly on water. There are some varieties that are very suitable for this, other varieties not. And yeah, you can use the water directly, and it's a very water efficient system. So it's interesting when you have issues with your clay soil or the hard pans in your soil, but it's also very interesting if you have a very limited amount of water, because water savings can be in the range of 50 up to 90% compared to open field cultivation. Next slide, please. So yeah, the trials are ongoing, and we don't focus on lettuce, but we focus on more commercial crops for the local conditions. So we're doing cauliflower, cabbage, pak choy, some beets as well. That seem very suitable for the saline conditions, and yeah, that's ongoing research, and yeah, as far as it's going, it's looking very promising as well. So this can also be linked to desalinization plants using the brine, and yeah, that can be very interesting applications as well. Next slide, please. So just to finish up, for us regarding the way forward concerning the cultivation aspect, so we really focus on the production in the field. Well, as said, it's really about an integrated approach, not only looking at your interactions with crop, soil, and water, but also the scale of your approach. If it works at field level, can you also make it work at farm and regional level? So those are our challenges still ahead that, of course, we want to collaborate with. So a lot of pilots and demos that we've done already show the practical possibilities on the field level. But yeah, to really make the integrated approach that you really go from demo to upscaling to impact, those are the next steps we want to make. And of course, to ensure the sustainable use of your saline resource sources, if you're using saline water for irrigation in the open field, well, of course, there are a lot of challenges. You can have good success in year 1 and year 2, but of course, you have to make sure that also in the long run, after 5 years, 10 years, 20 years, you still have a viable soil and a sustainable system. But for us also, the market potential to showcase that, really to convince farmers and the whole value chain, that's really important challenges still ahead for us as well. But in short, using saline resources is possible, and the work we've been doing now, it also shows it's profitable as well, and of course there's a big impact on food security and you name it. But in the end, farmers have to have a profitable cropping system, of course, so that's our initial focus. Thank you for now, and I hope we have some questions as well.
Thank you very much, Dr. Ake, for this presentation and these thoughts that you are sharing with us. I think now we come to the end of our workshop, but I have some questions. The first one for Nel, I think. There are a question regarding why we are planting mangrove in the seashores and not in the sea, and the purpose of growing the mangrove or to find the mangrove in the sea is to as a feed for the fish and the shrimps and laying egg there. So this is the purpose of the growing mangrove inside the seashores and not in the land out of the seas. So if you just would like to comment on that. Case, please. I think there are now we are discussing many plant species that could be as a candidate and approved candidate for growing in saline water or in seawater. Salicornia as an example, quinoa, and maybe some type of forages. You mentioned Suida fruticosa, I think, and one of the candidates that you are find that it is well salt tolerance. Can you just comment on this case and how far we will go with Suida fruticosa as a forage or another purposes in the production? Can you give Dr. Balgis the mic, please?
Okay. Yeah. I'm sorry. Could you please repeat?
About Suida fruticosa, I think you mentioned in your presentation that it is one of the candidate species that you will that you find that it is will be one of the candidate crop grown under saline or seawater farming. What is the future of this crop?
Yeah, we have already done, all the nutritive and anti-nutritive analysis of this fodder crop, as well as we had done animal trials. So right now, we had already successfully completed the plantation project at Balochistan hub site, and now I am starting a new project at Third Desert in Third Desert Sindh. So I believe this biosaline agriculture project would play a vital role in taking care of local communities of Tharparkar Desert and Balochistan areas and other arid regions and adjoining areas. Utilizing brackish water will reduce pressure on fertile lands and freshwater resources. So because I am working at the coal mining area and using the brackish water extracted from, for the coal mining operation. So we used that brackish water to for a plantation, and I hope our initial experiments gone well. So most probably we will get some good results here at her also.
Thank you. And I have a question for Dr. Argen just about the behavior and the production of the variety you are talking about as a forages, as vegetables. What is the comparative studies that you have seen when you compare the behavior of this crop under non-saline condition comparing with saline condition?
I'm not sure if I understand your question completely. That during the controlled field trials we did in the Netherlands, we used 6 different salt concentrations, so low salinity, moderate, high, so all these steps of salinity we used, and then just compare the growth response curve to your non-saline conditions. So that's about your relative yield. We look at the quality and that as well. So the components, the salinity levels of the parts that you're eating to make sure it's all safe, of course. And yeah, I'm not sure how to answer your question because I'm not sure how you mean with
talking about how we compare in a production level. In a production level, how these variety produce under non-saline and saline. I think in one slide you mentioned that you discovered that there are 42% increase in potato production in Pakistan as an example. With normal condition, it was 27 ton per hectare or something like this. So if this is the case, I think there are a stimulation of the salinity to this variety, and it's behave like halophytic species. This is the point. Is this true also in the open field when you compare it under hydroponic or something like this? This is the point.
In Pakistan, we compared it with the potato variety that is commonly used by the farmers. So we only compared the traditional variety to the more tolerant variety that we introduced. And that's where the 42% yield increase comes from. So we used different locations, but there was not a lot of differences in salinity levels. So it was more difficult to compare the different salinity levels. So in that case, it's more about comparing the local varieties with the newly introduced varieties and then see about the yield increase, the percentage. And in Egypt, that example was just the absolute yield. So we had different varieties and the best varieties showed this 32 ton per hectare yield. And we know from the official recordings in Egypt that the average potato yield is 27 tons per hectare. So in that case, we used just the government data on the average ton per hectare production and compared that with the potato variety we tested under field conditions.
For answering, in the end of that, I would like to thank all the participants for the outstanding presentation you made to tackle salinity in different regions of the world. The presence of high-level presenters, respectable attendees that actually make this event lively and interactive. I do agree with the speakers to explore and unlock new avenues of research like saline agriculture, particularly seawater farming, as one solution to feed everyone in 2050, and to minimize freshwater use only for essentials that eventually would contribute sustainability to our food system by securing food grains lost due to salinity. Therefore, we need to address the problems caused by soil salinization, that is losing at least 3 hectares of arable land every minute, by better management of fragile soil system through affordable, innovative solutions shared by the speakers, like eco-friendly conditioners such as the liquid natural clay or bio clay, and land-scale screening for tolerance conventional crops, identifying halophytes that can be used as food or fodder, edible oil, medicines, ornamental, fuel, and timber purposes, and establishing large-scale pilot projects to test and technologies and then their customization to be local conditions for better adaptation. The participant rightly mentioned the isolation of wild species, tolerance to salt, and then their genetic improvement by integrated holistic approaches involving genomics, physiology, and breeding is very much important to make salt tolerance plant more like crops with high germination tolerance and uniform maturity. Finally, we need to mobilize collaboration and develop partnership to develop integrated approaches and framework to integrate component and innovations for better implementation and upscaling and outscaling of seawater farming and saline agriculture. That is all we have from the international workshop on the future of seawater farming and saline agriculture in the Kingdom of Saudi Arabia. From my side and my entire team, take care of yourself. For more detail, you can always contact us and go to our Twitter link. Again, thank you so much for your active participation and fantastic contribution from all the speakers and the attendees. Wish you have a nice time. Goodbye and see you in next workshop. Thank you very much.